Hey there, night owls! Picture this. It's 1250-something in England. You're a peasant with approximately 0 coins to your name, and winter's coming in hot, or rather, brutally cold. No hardware store, no insulation from Home Depot, no YouTube tutorials on building a cozy cabin. Just you, some mud, sticks you found lying around, and the very real possibility of freezing to death before spring decides to show up. So here's the question that's keeping us up tonight. How did regular folks actually survive those bone-chilling medieval winters without modern materials? The answer involves techniques so clever they'd make today's architects pause and take notes. Before we dig into the dirt, literally go ahead and smash that like button if you're ready for some genuinely fascinating survival history, and drop a comment telling me where you're watching from. Seriously, are you in Toronto? Mumbai? Some tiny village in Norway? I want to know who's joining me for this journey into medieval engineering. Now dim those lights, get comfortable, and let's find out how our ancestors refused to become medieval popsicles. So let's set the scene properly, because understanding medieval English winters means throwing out pretty much everything you think you know about cold weather. We're talking about the 1250s here, smack in the middle of what historians cheerfully call the medieval warm period, which despite the name still featured winters that could absolutely kill you. The irony isn't lost on anyone. It's like calling a shark friendly, because it only bites sometimes. The thing about 13th century England is that it existed in this weird climate sweet spot that was warmer than the brutal little ice age that would come later, but still plenty cold enough to present serious survival challenges. We're looking at average winter temperatures hovering around freezing, dipping well below when the mood struck, with none of the modern conveniences that make cold weather merely annoying rather than actively life-threatening. No fleece-lined jackets from North Face. No emergency space heaters. No, I'll just turn up the thermostat solutions. Just you, the elements, and whatever shelter you could scrape together from the landscape. And here's where it gets interesting, because freezing to death wasn't some rare, tragic accident in medieval England. It was a legitimate concern that shaped literally every decision you made from September through March. The historical records are full of mentions of people found dead from exposure, livestock frozen in fields, and entire families huddling together for warmth in structures that modern building codes would condemn in about 17 seconds. One medieval chronicle from Oxfordshire casually mentions finding a travelling merchant frozen solid on the road, still clutching his walking stick, like this was just another Tuesday in February. Which honestly it kind of was. The dangers weren't just about the temperature itself, though that was bad enough. It was the combination of factors that turned winter into a genuine survival situation. You had the cold, obviously, but also the damp, that bone-deep, moisture-saturated cold that England does so well. The kind that seeps into everything and makes even moderately chilly temperatures feel absolutely miserable. Then add in the wind, which in medieval England had exactly 0 obstacles in its path across the landscape. No windbreaks. No carefully planted rows of trees. Just flat, open countryside where the wind could pick up speed and slam into your sad little dwelling, with all the enthusiasm of a battering ram. And let's talk about what winter actually meant in practical terms for a medieval peasant. It meant darkness. Lots of it. The sun set around 4 in the afternoon if you were lucky, and didn't bother showing up again until nearly 8 the next morning. That's right, you had tallow candles if you were doing well, or more likely just the dim glow from your fire if you could afford to keep one burning. Imagine trying to do literally anything productive in those conditions. Reading? Forget it. Detailed handwork? Good luck. You were basically in survival mode from October to April, just trying to make it through to spring with all your fingers and toes still attached. The wind chill factor, though medieval folks didn't have a name for it, was absolutely brutal. When you've got temperatures right at freezing, and then a 20-mile-per-hour wind comes howling across the fields, your body's experiencing conditions equivalent to well below 0. And your body doesn't care that the actual temperature is 32 degrees. It's losing heat faster than it can generate it, and that's when things get dangerous fast. Hypothermia doesn't wait around for dramatic sub-zero temperatures. It'll happily set in at temperatures that modern folks would consider merely chilly if you're wet, exhausted, and inadequately sheltered. The medical understanding of cold-related death was, unsurprisingly, somewhat lacking in the 13th century. People knew you could freeze to death, obviously, they'd seen it happen, but the mechanisms weren't exactly clear. They didn't understand that your body redirects blood flow away from extremities to protect vital organs, or that your core temperature dropping just a few degrees could shut down critical functions. They just knew that people who stayed outside too long in winter sometimes went to sleep and didn't wake up. which they attributed to various humoral imbalances or, depending on who you asked, divine judgment. Their solution was straightforward: don't stay outside. Build shelter. Stay warm. Survive. And surviving meant building, which brings us to the absolutely fascinating part of this whole story. The techniques and materials these people used to create structures that could actually keep them alive through months of hostile weather. Because here's the thing that always gets me. They didn't just survive. They developed sophisticated, clever, genuinely effective methods for creating shelter using basically nothing. And I mean nothing. No modern materials. No power tools. No YouTube tutorials on how to build a medieval house. Just local materials, accumulated knowledge, and the highly motivating factor of build this right or die. So let's talk about earth. Good old dirt. The stuff. But in medieval England, earth wasn't just the foundation for your house. It was often a significant portion of the structure itself. And this wasn't some primitive, desperate measure. This was sophisticated engineering that took advantage of the Earth's natural properties in ways that modern architects are only now rediscovering and getting all excited about. The basic principle behind Earth-based construction is almost stupidly simple, which is probably why it worked so well. Earth is an excellent insulator. It's dense, which means it absorbs heat slowly and releases it slowly. It's everywhere, which solves your material sourcing problem immediately. And it's extremely effective at blocking wind, which, as we've established, was a major concern in medieval England. You weren't going to get drafts through a wall that's literally made of compacted dirt. The wind could howl and rage all it wanted outside. Inside, you were protected by what essentially amounted to a cocoon of earth. Now, when we talk about earth-based medieval construction, we're not talking about just piling up dirt and hoping for the best. We're talking about a specific type of structure that archaeologists get very excited about. The sunken house, or as they're sometimes called in Old English, the Grubenhaus, which sounds much more dramatic than pit house, doesn't it? The Germans always had a flair for making things sound more impressive than they actually were. Here's how a sunken house worked. You'd start by digging down into the ground, typically about 1/2 metre to 1 metre deep, so roughly 18 inches to 3 feet, for those of us still clinging to imperial measurements. This wasn't random depth. It was carefully calculated based on local experience to get below the frost line, where the ground maintained a more stable temperature, while not going so deep that you hit groundwater and created yourself a medieval swimming pool, which, trust me, nobody wanted in winter. The excavation itself was usually rectangular, measuring anywhere from 3 to 5 metres long and 2 to 4 metres wide. So you're looking at spaces that were roughly 10 to 16 feet long and 6 to 12 feet wide. Not huge by modern standards, but adequate for a small family. These weren't meant to be palaces. They were meant to keep you alive, and they did that job remarkably well. Archaeological evidence for these structures is everywhere once you know what to look for. And I mean everywhere. Sites across England, particularly in the eastern and southeastern regions, are absolutely full of these sunken house remains. The beauty, you can't accidentally miss a big rectangular pit in your survey. It's sitting right there, usually filled with centuries of accumulated soil and debris, just waiting to tell its story. One of the most extensively studied sites is in West Stow in Suffolk, where archaeologists found evidence of an entire early medieval village featuring multiple sunken houses. And what's fascinating is that you can see the evolution of the technique over time. The earlier structures are simpler, more basic. Later ones show refinements, better drainage systems, more sophisticated roof support structures, evidence of experimental approaches to the same basic problem. These people were constantly iterating, improving, adapting their techniques based on what worked and what didn't, which is basically the scientific method, just without the peer-reviewed journals. The construction process for a sunken house started with that excavation, obviously, but the real skill came in what you did with that hole once you dug it. The floor of your sunken house needed to be compacted. Just loose dirt would turn into mud the first time you tracked in moisture, which in England was approximately 5 minutes after you finished digging. So you'd tamp down the earth, sometimes mixing in clay if your local soil was too sandy, or sand if it was too clay heavy. You wanted something that would pack firm and stay relatively dry. Drainage was critical. This is England we're talking about. It rains. A lot. Like a truly impressive amount. If you just dug a hole and called it a day, you'd have a pond, not a house. So medieval builders would typically excavate a slight slope toward one side of the structure, where they'd create a drainage channel that led away from the building. Sometimes they'd line this channel with stones or wooden planks to keep it from filling in. The whole system was designed to let water flow away from your living space rather than pooling inside it, which seems obvious until you realise how many modern basements still get this wrong. Once you had your hole properly prepared, the next step was establishing the roof structure. And this is where sunken houses get really clever. See, because you're already dug down into the earth, your walls are partially underground. This means you don't need tall posts to support your roof. It's already closer to the ground. Most sunken houses used a simple A-frame roof structure supported by posts at each end of the building. 2 sturdy wooden posts, usually oak if you could get it, driven deep into the ground at either end of your rectangle. Then a ridge beam connecting them across the top, and rafters extending down from that ridge beam to the ground surface. The beauty of this design is that the earth itself forms part of your walls. You might extend wooden planks or wattle panels up from the excavation edge to the roof line, creating a complete enclosure, but a significant portion of your wall space is just packed earth, which again is brilliant insulation. Modern earth-bermed homes use the exact same principle, surrounding the living space with earth to take advantage of that thermal mass and insulation value. Medieval peasants figured this out 1,000 years ago using nothing but observation and experience. The thermal properties of sunken houses are genuinely impressive. Earth maintains a relatively constant temperature once you get a bit below the surface, warmer than the air temperature in winter, cooler in summer. This means your sunken house starts with a baseline temperature advantage. While the air outside might be hovering right around freezing, the earth surrounding your walls is maintaining a temperature several degrees warmer. Add in a small fire for additional heat, and you've got a living space that's genuinely comfortable, or at least survivable, which was the goal. Wind protection was another huge advantage. Wind chill, as we discussed, was a major problem in medieval England. But wind can't blow through earth. Your sunken house, sitting partly underground with earth walls, was naturally protected from wind. The roof structure might catch some wind, roofs always do, but the living space itself was sheltered. And anyone who's ever stood outside on a windy winter day and then ducked behind a building knows exactly how much difference that makes. It's the difference between miserable and merely cold. Archaeological excavations have revealed just how common these structures were. At some sites, you find evidence of sunken houses being used alongside more conventional above-ground buildings, suggesting they served specific purposes. Some were workshops. The stable temperature made them ideal for crafts that required consistent conditions. Some were storage spaces, taking advantage of that cool, stable environment to preserve food. And yes, some were absolutely used as living spaces, particularly by families who couldn't afford the materials for a full above-ground house. The finds inside these sunken houses tell fascinating stories. At one site in Hampshire, archaeologists found loom weights and spindle whorls, suggesting the structure was used for textile work. Makes sense. Sitting slightly underground with good natural light from the doorway, protected from wind, would be an excellent place to work wool. At another site in Kent, they found storage vessels and evidence of grain processing, indicating the space served as a combination workshop and storage facility. The versatility of these structures was part of their appeal. What's really interesting is the evidence of repeated reconstruction on the same sites. You'll find locations where a sunken house was built, used for a generation or two, then rebuilt in almost exactly the same spot. Sometimes the new house is a bit larger, or the drainage system is improved, or the post holes are positioned slightly differently, but the basic location remains constant. This tells us these weren't temporary shelters or desperate measures. They were valued, proven designs that families returned to again and again because they worked. The social implications of sunken houses are worth considering too. These weren't the dwellings of nobles or wealthy merchants. These were working people's homes, farmers, craftspeople, the everyday folks who made up the vast majority of medieval England's population. The fact that they're so common in the archaeological record tells us that this building technique was accessible, practical, and widely understood. It wasn't specialised knowledge held by master builders. It was common sense architecture that anyone with a shovel and some basic skills could implement. But let's address the elephant in the room, or rather the moisture in the house. Living partially underground in England, where it rains approximately 6 days a week, sounds like a recipe for constant dampness. And that's a legitimate concern. The medieval builders weren't stupid. They knew about damp. They'd lived with it their entire lives. The solutions they developed were actually pretty sophisticated. First, location mattered enormously. You didn't just dig your sunken house anywhere. You looked for well-drained ground, preferably on a slight slope where water would naturally flow away. Sandy or gravelly soil was preferred over heavy clay, which held moisture. The medieval builder's rule of thumb was simple. If water pools there when it rains, don't dig there. Find somewhere else. Second, as mentioned, drainage systems were built into the structure from the start. That slight slope in the floor, the channels directing water away, sometimes even stone-lined sumps at the lowest point to collect and remove moisture. These weren't afterthoughts. They were fundamental elements of the design, recognized as essential to making the structure livable. Third, ventilation. You needed to let air circulate to prevent moisture buildup from cooking, breathing, and just general human occupation. Most sunken houses had doorways that could be left partially open during the day, and some evidence suggests smoke holes in the roof that served double duty as ventilation points. Fourth, and this is crucial, floor coverings. Nobody was living directly on packed earth. That would be damp and miserable. Instead, floors were covered with rushes, straw, or reeds, which were replaced regularly. These organic floor coverings absorbed moisture, provided insulation, and when they got too damp or dirty, you just gathered them up, tossed them out, and put down fresh ones. It's brilliant in its simplicity. Your floor covering is both insulation and a moisture control system, and it's made from materials that are freely available in any field or marsh. The archaeological evidence supports this. When they excavate sunken houses, they often find thick layers of organic material on the floors, decomposed straw and reeds compacted over years of use. Chemical analysis of these layers shows evidence of regular replacement, creating a stratified record of occupation. It's like reading tree rings, but instead of telling you about climate, they're telling you about medieval housekeeping habits. Now, modern experimental archaeology has really helped us understand how these structures performed in practice. Groups like the Westow Anglo-Saxon village have built full-scale reconstructions of sunken houses using medieval techniques. And then, this is the fun part, they've actually used them to see what living in them would have been like. They've held overnight stays in these structures during winter, monitored temperatures, tested different heating systems, and generally put the medieval design through its paces. And you know what they found? These things work. Remarkably well, actually. With just a small central hearth, the interior temperature of a sunken house stays noticeably warmer than the outside air. The earth walls really do provide significant insulation. Wind protection is excellent. Even on days when it's howling outside, the interior remains relatively calm. Moisture isn't the nightmare problem you might expect if drainage is properly designed and floor coverings are maintained. People have spent entire winter nights in these reconstructed structures and reported being quite comfortable, or at least as comfortable as you'd expect sleeping on a medieval floor to be. The thermal mass effect is particularly impressive. Earth heats up slowly and cools down slowly. This means that once you've warmed your sunken house with an evening fire, it doesn't immediately lose all that heat the moment the fire dies down. The earth walls absorb heat and radiate it back slowly through the night. It's passive heating, using principles that modern passive house design is only now getting really serious about. Medieval builders understood this intuitively through experience. They didn't have thermodynamics equations, but they knew that houses dug into the earth stayed warmer with less fuel, and that was all the proof they needed. The fuel efficiency aspect is worth emphasizing because fuel, meaning wood, wasn't infinite. England in the 1250s had plenty of forests, but gathering firewood was labor-intensive work. Every log you burned was a log you or someone in your family had to find, cut, and haul back to your dwelling. Efficient use of fuel wasn't just an environmental concern or an economic calculation, it was a survival necessity. A structure that stayed warm with less fuel meant more time for other work, less exposure to the elements while gathering wood, and better chances of your fuel supplies lasting through the winter. Sunken houses delivered on that efficiency promise. Compared to an above-ground structure with the same floor space, a sunken house needed significantly less fuel to maintain comfortable temperatures. Some modern estimates suggest as much as 30 to 40% less fuel consumption, though exact numbers are hard to pin down because it depends on so many variables: outside temperature, wind conditions, how well the structure is sealed, the size of your fire, and so on. But the principle holds: less heat escapes through earth walls than through wooden or wattle walls, so you need less heat generation to maintain comfortable conditions. There's also something to be said for the psychological comfort of a sunken house. When you're hunkered down, slightly below ground level with earth walls surrounding you and a warm fire burning, you feel protected in a way that's hard to describe. It's primal. It's the same instinct that makes modern people love cozy dens and basement rec rooms. There's something fundamentally comforting about being surrounded and sheltered. For medieval folks facing months of harsh weather, that psychological element wasn't trivial. Feeling secure in your shelter probably contributed to actually being secure, simply by reducing the stress and anxiety that came with winter survival. The construction timeline for a sunken house is another point worth considering. We're not talking about months of construction. With a few able-bodied workers and decent weather, you could dig and build a basic sunken house in a matter of weeks. The excavation itself for a standard-sized structure might take 2 or 3 people a few days of hard work. The post and beam structure could go up in a few more days. The roof covering, usually thatch, which we'll get to later, took longer because it required more specialised skill, but even that wasn't months of work. You could reasonably have a completed livable sunken house in under a month if you pushed hard and had help. This construction speed had real implications for medieval life. If disaster struck, fire, flood, structural failure, a family wasn't facing years of homelessness while they slowly accumulated resources to rebuild. They could, with community help, have a new shelter up in weeks. This resilience, this ability to rebuild quickly using locally available materials and widely distributed skills, was a crucial survival mechanism for medieval communities. Houses weren't permanent investments requiring decades to recoup. They were renewable resources that could be replaced as needed. Of course, not all sunken houses were purely earth-walled. As the technique evolved, builders experimented with hybrid designs. You might have earth walls on 3 sides for insulation and wind protection, with a wooden wall on the 4th side featuring a proper door and maybe a window. Or you might line the interior of your earth walls with wooden planks to create a smoother surface, an additional insulation layer. Some higher status sunken houses show evidence of stone footings and more elaborate post and beam structures, turning them into something more like modern basements with wooden superstructures on top. The archaeological site at Catholm in Staffordshire shows a particularly interesting example of this hybrid approach. Excavations there revealed sunken houses with partial stone walls, suggesting either higher status occupants or a later evolution of the basic design. The stone provided additional structural support and perhaps a bit of status signalling. Look at us, we can afford to incorporate stone into our house, while still maintaining the thermal advantages of earth-bermed construction. Regional variations in sunken house design are fascinating too. In areas with rockier soil, excavations were shallower, and builders compensated by building up earth berms around the above-ground portions of the walls. In wetland areas, drainage systems were more elaborate, sometimes including wooden water management structures that would make modern civil engineers nod in approval. Coastal areas show evidence of sunken houses with additional wind protection measures, thicker roof structures, more substantial post and beam frameworks, anything to help them survive the absolutely brutal winds that came howling off the North Sea. The transition away from sunken houses in later medieval periods tells its own story. As England's economy developed and building materials became more readily available and affordable, above-ground timber frame structures became more common. This wasn't because sunken houses didn't work. They absolutely did. It was more about changing priorities and possibilities. Timber frame houses offered more vertical space, were easier to expand, and frankly carried more social status. There was a certain we've made it quality to living fully above ground in a proper house with real walls. But the knowledge didn't disappear entirely. Into the 14th and 15th centuries, you still find sunken structures being built and used, particularly for specialized purposes. Workshops, storage buildings, and seasonal shelters continued using the basic sunken house principles because they remained practical and effective. Some farming communities used them for livestock shelter. That same thermal protection that kept humans comfortable worked equally well for valuable animals. What strikes me about the whole sunken house tradition is how it represents a perfect example of appropriate technology. These weren't crude, primitive shelters thrown up by people who didn't know any better. They were carefully designed structures that took maximum advantage of available materials and natural principles to solve a genuine survival problem. Medieval, they just expressed that understanding through practical building rather than mathematical equations. And here's something modern architects are only now widely acknowledging. Those medieval builders were often right. Earth-bermed construction works. Modern passive houses and sustainable architecture movements are increasingly incorporating earth as a building material and design element, rediscovering advantages that medieval peasants took for granted. We've spent centuries viewing underground or partially underground living as primitive and backwards, but the joke's on us. It was actually sophisticated and efficient all along. The archaeological evidence keeps accumulating too. Every construction project in England that involves digging has the potential to uncover more sunken house remains. A new housing development in Essex turns up 3 previously unknown structures. A utility line installation in Norfolk reveals a whole cluster of them. Each find adds to our understanding of how common these structures were how they were used, and how they evolved over time. The picture that's emerging is of a medieval England where earth-based construction was far more prevalent and sophisticated than traditional histories acknowledged. For the families living in these sunken houses through those harsh 13th century winters, the structure wasn't a curiosity or an interesting archaeological feature. It was home. It was survival. It was the difference between making it through to spring or becoming another tragic note in some chronicle. And they made it work using nothing but dirt, wood, thatch, and accumulated knowledge passed down through generations. The effectiveness of earth as a building material in medieval England challenges our assumptions about progress and development. We tend to think of history as a linear progression from primitive to advanced, from crude to sophisticated. But standing in a reconstructed sunken house on a cold winter day, feeling how effectively it shelters you from the wind and cold, you realize that sometimes the primitive solution is actually the smart solution. Medieval builders weren't using earth because they were too unsophisticated for real building materials. They were using earth because it worked incredibly well for their needs and their circumstances. This distinction matters because it changes how we understand medieval life. These weren't desperate people barely clinging to existence. They were clever, skilled individuals who developed effective solutions to their environmental challenges. The fact that those solutions look different from what we might choose today doesn't make them inferior. It makes them adapted to different circumstances and resources. That's not primitive. That's smart. So as we move forward into exploring the other elements of medieval shelter construction, the wooden frameworks, the wall techniques, the roofing systems, keep in mind this fundamental principle that earth-based building demonstrates. Medieval builders were solving complex problems with elegant, effective solutions using available resources. They were engineers. They were innovators. They were people who understood their environment and worked with it rather than against it. And honestly, more than a few modern architects could stand to take notes. Now, while sunken houses were brilliant for what they were, they had their limitations. You couldn't really build up with them. You were stuck with that low-profile, semi-underground design, which was great for thermal efficiency but not so great if you wanted, say, to stand up fully in the middle of your house without hunching over like Quasimodo, or if you wanted to store things vertically, or if you just felt like having a house that looked like a house rather than a particularly well-organized hole in the ground. Enter the cruck frame construction, which is honestly one of those medieval innovations that doesn't get nearly enough credit in the popular imagination. We all know about Gothic cathedrals with their flying buttresses and pointed arches. Those get all the attention, all the tourism dollars, all the dramatic lighting in history documentaries. But cruck frame buildings? They're the unsung heroes of medieval architecture, the structures that actually housed the majority of England's population, and did so with remarkable efficiency and clever engineering. The term cruck comes from the Old English word crook, which should give you a pretty good hint about what we're dealing with here. We're talking about curved wooden beams, naturally curved, taken from trees that grew in specific ways, used as the primary structural elements of a building. Imagine a wishbone if wishbones were made of oak and stood 15 feet tall. That's your basic cruck frame. Two curved timbers that start wide at the ground level, sweep upward and inward, and meet at the top to form the peak of your roof. It's elegantly simple, structurally sound, and uses wood in a way that actually takes advantage of how trees naturally grow rather than fighting against it. And here's where it gets interesting from an engineering perspective. Each pair of crucks, and you'd have multiple pairs running the length of your building, formed what's essentially a self-supporting arch. You didn't need complex calculations or elaborate buttressing systems. The curved timbers naturally directed force downward and outward to the ground where they were secured. It's the same principle that makes arches so stable, just achieved through a different form. Medieval carpenters understood structural mechanics in a deep, intuitive way that came from generations of trial and error, success and catastrophic failure. The search for the right timber was practically an art form in itself. You couldn't just wander into the forest, point at a straight tree and call it a day. You needed to find trees that had grown with a natural curve. Usually this meant looking for trees that had grown on slopes or in conditions that caused them to bend as they grew. Oak was the preferred choice because it's incredibly strong and durable, though ash and elm sometimes made appearances depending on local availability. The ideal cruck timber had a gentle, even curve that spanned somewhere between 15 and 25 feet in length. Finding matching pairs was the real challenge. You needed two timbers with essentially mirror image curves so that when you set them up opposite each other, they'd form a symmetrical frame. This wasn't a weekend project. Carpenters would sometimes spend months scouting forests, marking potential trees, waiting for the right time to fell them. There are medieval documents that mention disputes over particularly good crux timber, people literally fighting over who had rights to specific curved trees. When your entire building technique depends on finding naturally curved wood, access to the right trees becomes serious business. The felling process had its own rituals and timing. Medieval builders preferred to cut timber in winter when the sap was down, believing, correctly as it turns out, that winter-cut wood was less prone to splitting and warping as it dried. They'd select their trees, fell them carefully to avoid damaging the valuable curve, and then begin the process of converting raw timber into building components. This involved stripping bark, rough shaping with axes and adzes, and then allowing the wood to season, which could take months or even years depending on the thickness of the timber and local climate. Here's some. The crux frames were assembled flat, all the joints cut and tested, all the pieces fitted together to make sure everything worked. Only then did they raise the frames into position. This was partially practical. It's much easier to work on something when it's at ground level rather than balancing on a ladder 20 feet up. But it also meant you could catch and correct mistakes before you'd committed to lifting several £100 of oak into the air. The joints used in crux frame construction are where you really see the sophistication of medieval carpentry. We're talking about mortise and tenon joints, lap joints, and various forms of notched connections, all cut by hand with tools that would look primitive compared to modern power equipment, but were, in skilled hands, capable of astonishing precision. A good medieval carpenter could cut a mortise and tenon joint that fit together so tightly you could barely see the seam. No gaps, no wobbling, just solid wood-to-wood contact distributing loads exactly where they needed to go. The mortise and tenon joint, for those not familiar with traditional woodworking, consists of a cavity, the mortise, cut into one piece of wood, and a projection, the tenon, cut on another piece that fits into that cavity. When properly made, it's an incredibly strong connection. The tenon is usually about 1/3 the thickness of the stock it's cut from, with shoulders that seat against the mortise piece to prevent twisting. Medieval carpenters would often secure these joints with wooden pegs, oak pegs driven through holes drilled through both pieces once the joint was assembled. These pegs swelled slightly as they absorbed moisture, locking the joint even more firmly. The beauty of these wooden joints, and why medieval builders relied on them almost exclusively rather than nails or metal fasteners, comes down to a few factors. First, metal was expensive. Really expensive. Nails had to be hand-forged by blacksmiths, which meant they cost actual money, and medieval peasants were not exactly flush with disposable income. A single iron nail represented a significant investment. Building an entire house frame with metal fasteners? That was for wealthy people with pretensions. Everyone else used wood to join wood, and it worked just fine. Second, wooden joints actually perform better than nails for major structural connections. A properly cut mortise and tenon joint distributes force across a much larger surface area than a nail, which just creates a single point of stress concentration. Wooden joints can flex slightly as the timber moves with temperature and humidity changes, and wood always moves, without failing. Nails in the same situation would work loose or the wood would split around them. The medieval carpenter who chose wooden joints over nails wasn't being primitive, they were being smart. Third, and this is something that becomes relevant when your building needs repairs or modifications, wooden joints can be disassembled. You pull the pegs, separate the timbers, make your changes, and put everything back together. Try doing that with medieval nails, which were typically clinched over on the backside. You'd destroy the materials trying to take them apart. The wooden joint tradition meant buildings were adaptable, repairable, and renewable, in ways that nailed construction simply wasn't. The raising of a crux frame was a community event, and not just because it was a good excuse for a party, though it definitely was that too. You needed people. Lots of people. A single crux frame, 2 curved timbers plus the ridge beam connecting them at the top, could easily weigh several £100. Getting it from horizontal on the ground to vertical, and in position required coordinated effort from a team of workers. They'd typically use ropes and poles as levers, with some people pushing, others pulling, everyone working together to walk the frame up into position without dropping it, which would be disastrous on multiple levels. Imagine the scene. You've got your 2 crux timbers laid out, connected at the apex by a ridge beam. The whole assembly is resting on the ground on what will become its back side. The front side is pointing up at the sky. Ropes are... Teams of workers grab these ropes. Others position themselves along the frame with poles to help push and guide. Someone, usually the master carpenter, calls out the rhythm. On his signal, everyone pulls or pushes together. The frame begins to tilt upward. Slowly, carefully it rises. As it approaches vertical, workers rush in to set the base of the crux into their prepared positions. Sometimes this meant slots cut in foundation beams, sometimes actual holes dug in the ground. The moment when a crux frame locks into place vertical must have been satisfying in a deep primal way. And then you'd do it again for the next frame. A typical crux frame building might have anywhere from 3 to 6 pairs of crux running down its length, each one requiring this same raising process, each one needing to be properly aligned and spaced. The spacing between crux frames, called bays, was determined partly by the length of available timber for horizontal members and partly by the span capabilities of the roofing material. You'd typically see bays of 12 to 16 feet, which was about as far as you could span with medieval roof timbers without worrying about excessive sagging. String too many 16-foot bays together and you've got yourself a respectable building. 3 bays gave you a structure roughly 45 feet long. 4 bays, 60 feet. These weren't tiny houses. Once your crux frames were up and secured, the rest of the structure went together relatively quickly. Horizontal members called purlins ran between the crux, parallel to the ridge beam, creating the framework that the roof covering would attach to. Wall plates ran along the top of the crux feet at ground level, tying everything together and providing attachment points for the wall sections. Collar beams might span between the 2 sides of individual crux, creating additional bracing and sometimes providing a base for an upper floor or loft space. The result was a structure that looked from the inside like being inside the ribcage of some enormous wooden beast. Those curved crux timbers rising from the ground, arching over your head, created a space that was both organic and geometric. It felt sheltering in a way that flat-walled, right-angled modern buildings somehow don't. There was a reason medieval people carved elaborate decorations into their crux timbers when they could afford it. These weren't just structural elements, they were the defining visual feature of your living space. The load distribution in a crux frame building is genuinely clever. The weight of the roof comes down through the purlins to the crux, which channel that force down to the ground. Because the crux are curved, the outward thrust at the base, the force trying to push the walls apart, is significantly reduced compared to a straight rafter system. This meant you didn't need massive foundations or complicated buttressing systems. Your job was just to help it do what it naturally wanted to do and prevent it from shifting laterally. Medieval carpenters marked their timbers with assembly marks, Roman numerals, tally marks, or geometric symbols carved into the wood, to keep track of which piece went where. This was crucial because, remember, all the fabrication was done on the ground, often at a different location from where the building would be raised. You might have a carpenter's yard where all the cutting and fitting happened, and then you'd transport the components to the actual building site. Without clear marking systems, you'd be trying to figure out which of 3 apparently identical purlins was supposed to go in which bay, and trust me, they were not identical even if they looked it. Each joint was custom fitted to its specific location. Archaeological examinations of surviving crux frame buildings, and yes, there are still medieval crux buildings standing in England, which is pretty remarkable when you think about it, reveal fascinating details about construction sequence and technique. You can see where carpenters made mistakes and corrected them. You can find abandoned mortises where someone started cutting a joint in the wrong location and had to start over a few inches away. You can trace the marks of different tools, identifying whether an adze or an axe or a saw made a particular cut. It's like reading the biography of a building written in wood. The durability of crux frame construction is honestly impressive. When properly maintained, and that's a crucial qualifier, these structures could last centuries. There are crux buildings in England that date back to the 14th century and are still functional today. 600 years. That's not because medieval builders had better materials than us. Oak is oak whether you cut it in 1350 or 2025. It's because they understood how to use that oak in ways that worked with the material's properties rather than against them. The main enemy of timber frame buildings, medieval or modern, is water. Specifically, water that gets into the wood and creates conditions for rot fungi to establish themselves. Medieval builders understood this perfectly well, even if they didn't know about fungal spores and decomposition chemistry. They knew that wood that stayed wet rotted, and rotted wood was structurally useless. So they developed strategies to keep their timbers dry. The first strategy was getting the wood up off the ground. The feet of crux frames typically rested on stone pads or foundation beams that themselves sat on stone. This created a barrier between the wood and the damp earth. Even a few inches of elevation made a huge difference in longevity, because it prevented ground moisture from wicking up into the timber through capillary action. Some buildings use stone walls for the first foot or two of height, with the wooden structure starting above that, which gave even better protection. The second strategy was roof overhang. A cruck frame building typically had significant roof overhang projecting beyond the wall line. This meant that rain running off the roof landed well away from the base of the walls and the cruck feet. It's simple physics. The farther from the building the water lands, the less chance it has to splash back or soak into the ground right next to your structure. Some medieval buildings had roof overhangs extending 2 or 3 feet beyond the wall line, which seems excessive until you remember that they didn't have gutters and downspouts to manage roof runoff. The third strategy was treatment. Medieval builders used various substances to protect timber from the elements. Oak tar was popular. It's naturally antiseptic and water-resistant. Linseed oil mixed with various additives provided another protective coating. Some builders would char the surface of timbers that would be in contact with stone or earth, creating a layer of carbonized wood that was much more resistant to decay than raw wood. These weren't just folk traditions, they were empirically tested methods that extended timber life significantly. But even with all these protections, repairs were inevitable. A 600-year-old building didn't make it that long without maintenance. Medieval buildings were constantly being repaired, modified, and updated. A rotten cruck foot would be cut off and the timber set on a new stone pad. Failed joints would be reinforced. Sections of wall would be rebuilt. This was accepted as normal. Buildings were living things that required ongoing care, not static objects that you built once and forgot about. The social implications of cruck frame construction are worth considering. These buildings required skill to design and build, but that skill was distributed widely through medieval society. Most villages would have at least one carpenter who understood cruck frame principles. Larger towns might have several, along with specialized workers for different aspects of the construction. This meant that housing construction wasn't dependent on a small class of elite master builders. It was accessible to ordinary communities who could raise a building through collective effort. The community raising aspect created social bonds and obligations. If the village helped raise your cruck frames, you were expected to help when it was someone else's turn. This mutual aid system meant that even relatively poor families could achieve adequate housing, because labour costs, the biggest expense in any building project, were effectively shared across the community. You didn't need to save up to pay a professional crew. You needed to be part of a community that helped each other, which was a different kind of currency entirely. Regional variations in cruck frame design are fascinating. In the West Midlands, you tend to find what are called full crucks, where the curved timbers run from ground level all the way to the ridge beam in one continuous piece. In other areas, base crucks were more common. These only extended partway up the wall before being joined to straight rafters that continued to the ridge. Some regions favoured steeper roof pitches, others shallower. These variations reflected local timber availability, regional building traditions, climate factors, and probably a fair bit of "this is how we've always done it" conservatism. The transition from base crucks to full crucks to box frame construction over the medieval period shows technological evolution in action. Base crucks were probably easier to source, you needed shorter curved timbers, but full crucks created more interior height and better structural geometry. Box frame construction, which came later, used straight timbers throughout and created more flexible interior spaces at the cost of requiring more complex joinery and bracing. Each system had advantages and trade-offs, and medieval builders chose based on their specific needs and resources. The interior space of a cruck frame building had a particular character. Those curved timbers sweeping overhead created a sense of enclosure without feeling cramped. The natural curves of the wood were visually softer than straight beams and right angles. Light and shadow played across the curved surfaces in interesting ways. If you've ever been inside a surviving medieval cruck building, and if you ever get the chance, take it. There's something about the space that feels fundamentally different from modern construction. More organic, more connected to natural forms. From a practical standpoint, cruck frames solved the fundamental problem of how to create significant enclosed space using available materials and technology. You needed shelter from the elements. You needed it to be sturdy enough to survive storms, snow loads, and time. You needed to build it with tools and techniques available to ordinary people. Cruck frames delivered on all these requirements elegantly. They were the appropriate technology for their time and place, which is the highest praise you can give any solution. The engineering loads in a cruck frame building are worth understanding because they explain why the system works so well. Start with dead load. That's the weight of the structure itself. The cruck timbers, the purlins, the ridge beam, the roofing materials, all of that creates a constant downward force. The curved shape of the crux channels this force down to the ground naturally. Then you have live loads, things like snow accumulation on the roof, or people moving around if there's an upper floor or wind pressure. These variable loads also get channeled through the structure to the ground, but their distribution changes based on conditions. The curved crux acting as an arch is what makes the whole system stable. When snow piles up on the roof, that weight pushes down on the purlins, which transfer it to the crux, which compress along their length and transfer the force to the ground. The curve means that the force is always being directed along the timber, rather than trying to bend it, which is much more structurally efficient. Wood is very strong in compression along the grain. You can stack enormous weight on a vertical timber before it fails. It's much weaker when you try to bend it across the grain. The crux design takes advantage of wood's compression strength while minimizing bending forces. Medieval carpenters didn't think about forces and vectors the way a modern structural engineer would. They didn't calculate load distributions or draw free body diagrams, but they understood through experience and apprenticeship training how structures behaved. They could look at a timber and know if it was thick enough for the span it needed to cross. They could evaluate a curve and determine if it would work as a crux or if the geometry was wrong. This practical, experiential knowledge was incredibly sophisticated, even if it wasn't formalized into mathematical theory. The tools used in crux frame construction were, by modern standards, absurdly simple. Axes for rough shaping, adzes for smoothing surfaces, augers for drilling holes, chisels for cutting mortises, saws for cross-cutting, though medieval saws were relatively crude and mostly used for smaller work. A medieval carpenter's entire toolkit could fit in a single chest, and probably weighed less than a modern circular saw. Yet with these basic tools, they created structures that have lasted half a millennium. The skill lay not in the tools, but in the user. Learning to cut a clean mortise by hand takes practice. Learning to sharpen your tools properly so they actually cut cleanly, rather than crushing and tearing the wood fibers, takes time. Medieval carpenters typically apprenticed for 7 years, which seems excessive until you realize how much tacit knowledge had to be transferred. You couldn't learn this from a book. Books about carpentry technique basically didn't exist in forms accessible to working carpenters. You learned by watching, doing, failing, and eventually succeeding under the guidance of someone who'd been through the same process. The preservation of medieval carpentry knowledge is spotty. Some of it was written down in later centuries as craft guilds developed more formal training systems. Some survived in oral traditions passed from master to apprentice. Some was simply lost as building techniques changed and old methods fell out of use. Modern researchers trying to understand medieval carpentry often work backward from surviving buildings, examining the physical evidence and trying to deduce the processes that created it. It's architectural archaeology, piecing together lost knowledge from remnants. Experimental archaeology has contributed enormously to our understanding of crux frame construction. Groups have built full-scale crux buildings using only medieval tools and techniques, documenting every step of the process. These experiments reveal things that you can't learn from examining old buildings. How long does it actually take to cut a mortise by hand? How many people do you need to raise a crux frame safely? What does fresh-cut oak smell like when you're shaping it with an adze? These experiential details matter because they help us understand not just what medieval builders did, but what their working life was actually like. The results of these experimental builds confirm that crux frame construction was both practical and efficient given medieval conditions. A small team of skilled workers could frame a building in a matter of weeks. The techniques didn't require extraordinary strength. Proper leverage and good tools were more important than brute force. The structures that resulted were genuinely sturdy and functional. This wasn't desperate, crude building by people who didn't know better. It was competent, appropriate engineering by people who understood their materials and their needs. One aspect that often surprises modern people is how much a medieval timber frame building could move without failing. Wood is flexible. Joints allow for some movement. A crux frame in a strong wind would actually flex and sway slightly, which sounds alarming but is actually exactly what you want. Rigid structures under dynamic loads, like wind gusts, have to absorb all that energy internally, which creates stress concentrations that can cause failure. Flexible structures dissipate energy through movement. They bend rather than break. Medieval builders understood this intuitively and built structures that were resilient rather than rigid. The sound of a medieval crux frame building in a storm must have been quite something. Timbers creaking as they flexed, wind whistling through gaps in the wall coverings, rain drumming on the thatch roof. Maybe the occasional louder crack as a joint settled or a beam took up a new load. Inside, you'd feel the slight movement, see the timbers flexing overhead. It would be unnerving if you didn't trust the structure, but medieval people grew up in these buildings. They knew what normal movement sounded and felt like versus what indicated actual problems. Their sensory awareness of their building's condition was probably much more acute than ours is today with our static modern construction. The versatility of cruck frame design meant it could be adapted to many purposes. Houses, obviously, were the most common application. But you also find barns, workshops, churches, any structure that needed to enclose significant space. The principles scaled reasonably well. A small cottage might have just 3 cruck pairs, creating a cozy, compact space. A large barn might have 7 or 8 pairs, creating a structure big enough to store a year's harvest and shelter livestock. The technology worked across a range of scales. Status differentiation in cruck buildings came not from the basic structural system, everyone used crucks, but from the size, quality of materials, and finished details. A wealthy merchant's house might have larger, more perfectly matched crucks, finer joinery, and decorative elements carved into the timbers. A poor peasant's cottage would have smaller, perhaps less perfectly curved crucks, rougher joinery, and no decorative work. But both use the same fundamental structural principles. The physics of curved timber acting as an arch doesn't care about your social class. The decline of cruck frame construction in later centuries wasn't because the system failed or was inadequate. It was because alternatives became available and fashionable. Box frame construction with straight timbers allowed for more regular interior spaces and was easier to modify. Eventually, brick and stone became more affordable and carried more social prestige. Cruck frames came to be seen as old-fashioned, rustic, lower class. By the 17th century, new cruck construction had largely ceased, though existing cruck buildings continued to be used and maintained for generations. The newer technology isn't necessarily better in any objective sense. It's just different, and often more aligned with changing social values or economic conditions. Cruck frames worked perfectly well for their intended purpose, right up until people decided they wanted something different. The buildings themselves stand as testament to the skill and knowledge of their builders, even if those builders never got the recognition that, say, cathedral architects received. Walking through the English countryside today, you can still spot cruck frame buildings if you know what to look for. That characteristic curved shape of the roofline. The particular proportions of the structure. Sometimes, if you're lucky, you can peek inside and see the actual cruck timbers still doing their job 6 centuries after they were cut. It's a direct, tangible connection to medieval life. Someone in the 1300s walked through a forest, found those trees, cut them down, shaped them, raised them into position, and created a space that has sheltered humans ever since. That's not primitive technology. That's impressive engineering and a legacy that deserves respect. So you've got your beautiful cruck frame standing there, all those curved oak timbers arching overhead like the ribcage of a wooden whale. Fantastic. Very structural. Very impressive from an engineering standpoint. There's just one small problem. It's completely open to the elements. Wind blows straight through. Rain comes in from every direction. Snow drifts happily into what's theoretically the interior of your house. You've basically built an elaborate wooden skeleton, and now you need to put some skin on it. Enter wattle and daub, which is probably the most underappreciated building technology in human history, and also sounds vaguely like a firm of Victorian solicitors. Wattle and daub is at its core absurdly simple. You weave sticks together to create a basket-like panel, then you smear mud all over it. That's it. That's the entire technology in one sentence. But as with most things that sound simple, the devil is in the details, and medieval builders had refined those details over centuries into a technique that was remarkably effective, surprisingly durable, and, this is the part that would make modern building inspectors nervous, involved materials you could literally gather from your backyard. The wattle part refers to the woven stick framework. Think of it as basketry, but vertical and structural rather than horizontal and container-shaped. The basic principle is identical to basket weaving. You have vertical elements called stakes or staves, and you weave horizontal elements called withies or weavers between them, creating a tight matrix of interlaced wood. The result is a panel that's reasonably rigid, quite strong for its weight, and provides an excellent substrate for the daub that comes next. Let's start with the material selection for wattle, because this is where you see medieval builders' deep understanding of their local environment. The preferred material was willow, specifically young willow shoots harvested during their dormant season. And there were very good reasons for this preference that go beyond it was available, though availability certainly helped since willow grows like an aggressive weed anywhere there's moisture in England, which is to say everywhere in England. Willow has this wonderful property called flexibility. When it's fresh cut, especially if you harvest it in winter when the sap is down, you can bend it into surprisingly tight curves without breaking. This flexibility is crucial because you're going to be weaving these shoots between vertical stakes, bending them back and forth, and you need them to cooperate rather than snapping every time you change direction. Willow cooperates. It bends. It weaves. It's the ideal material for wattle work, which is why basket makers have been using it for approximately forever. Hazel was another popular choice, particularly in areas where willow was less abundant. Hazel has similar properties: flexible when green, strong when dry, grows in convenient straight shoots. Oak could be used for the vertical stakes because oak is strong and durable, though it's less flexible than willow, so it was rarely used for the weavers. Ash sometimes made appearances. Really, almost any wood that grew in long, straight, flexible shoots could potentially work, but willow and hazel were the gold standard. The harvest timing for wattle material was critical. You wanted to cut during winter dormancy, typically between November and March, when the sap had retreated down into the roots. Wood cut during this period was less likely to shrink and warp as it dried, and it was also easier to work with because the reduced moisture content made it lighter to transport and handle. Medieval coppicing traditions, cutting trees back to stumps so they'd produce multiple straight shoots, were partly about managing woodland resources, but they were also about ensuring a steady supply of perfect wattle material. Coppiced willow or hazel would produce shoots that were typically 6 to 10 feet long and anywhere from half an inch to 2 inches in diameter. That's your sweet spot for wattle work. Too thin and they'd lack structural strength. Too thick and they'd be difficult to weave and unnecessarily heavy. The medieval builder's eye could assess a stand of coppiced willow and immediately know which shoots were ready for harvest and which needed another season's growth. The processing of wattle material was minimal, which was part of its appeal. You cut your shoots, trimmed off any side branches, and that was about it. Some builders would strip the bark, believing it helped the wood dry more evenly and reduce the chance of insect infestation. Others left the bark on, arguing it provided additional protection and didn't really matter since it would all be covered in daub anyway. Medieval, they were arguing about bark removal techniques the way modern contractors argue about which brand of screws is superior. The construction of wattle panels started with installing the vertical stakes. Remember your timber frame structure, those cruck frames and horizontal members? There would be grooves or holes cut into the horizontal timbers, typically spaced every 6 to 12 inches depending on the design. The vertical stakes were installed into these holes, creating a grid of uprights that would form the foundation of your wattle panel. These stakes were usually thicker than the weavers, maybe 1 inch to 2 inches in diameter, and needed to be sturdy because they'd be bearing the weight and tension of the entire woven structure. Getting the stakes properly installed required some precision. Too loose and they'd wobble and shift as you wove, creating a sloppy, weak panel. Too tight and you'd split the timber trying to force them in. The ideal fit was snug. The stake held firmly but not so tightly that the wood was stressed. Medieval carpenters would sometimes shape the ends of stakes to fit their holes more precisely, or use wedges to secure them once installed. The goal was a stable framework that wouldn't shift during the weaving process. Now comes the fun part, the actual weaving. You'd start at the bottom of your panel with your first weaver, which was typically one of the longer, more flexible willow shoots. The technique is simple in concept. You pass the weaver in front of one stake, behind the next, in front of the third, and so on across the panel. When you reach the end, you bend the weaver back and start your return journey. But here's the key, you alternate the pattern. The stake that was in front on the first pass is now behind on the second pass. This creates the classic over-under basketry pattern that locks everything together. The reality of weaving wattle is messier than the description suggests. Willow shoots are not uniform. They taper from thick to thin. They have natural curves and bends. They have minds of their own about which direction they want to go. Medieval wattle weavers developed an intuitive sense for working with these irregularities. You'd orient your weavers so the thick ends and thin ends alternated, keeping the panel thickness relatively consistent. The weaving went faster than you might expect once you got into the rhythm of it. An experienced wattle worker could complete a panel several meters long in a day, working steadily but not frantically. The repetitive motion, grab a shoot, thread it through, bend it back, thread it back, had a meditative quality that numerous modern experimental archaeologists have commented on. It's absorbing work that requires attention but not intense concentration, leaving your mind free to wander while your hands stay busy. Probably a lot of medieval gossip got exchanged during wattle weaving sessions. As the panel grew higher, the weaving got trickier. You're reaching above your head now, trying to maintain even tension on chutes that are getting springy and difficult to control. Sometimes workers would use temporary bracing to hold the panel stable as they worked on the upper sections. Sometimes the collaborative aspect of medieval building shows up in these small details, tasks that were theoretically possible for one person to do alone but went much faster and better with help. The top of the wattle panel needed special attention. You couldn't just let your lace weaver in randomly in mid-panel. Ideally, you'd tuck the ends back into the weaving, or secure them with some kind of binding to prevent them from working loose. The vertical stakes usually extended above the top weaver by a few inches, then were trimmed flush or secured into another horizontal frame member. The goal... Now let's talk about daub, which is where things get viscerally medieval. Daub is mud, but it's engineered mud, if you will. Mud that's been carefully formulated to have specific properties: adhesiveness, workability, durability, and reasonable drying characteristics. The basic recipe hasn't changed much over centuries because it works. You take clay soil, you add fibrous material for reinforcement, you mix in some amount of water to get the right consistency, and you might add various other ingredients depending on what you're trying to achieve and what's available locally. Clay is the critical base ingredient because of its unique properties. Clay particles are tiny, much smaller than sand or silt, and they have a plate-like structure that gives clay its characteristic stickiness when wet. This stickiness is exactly what you want in daub because you need it to adhere to the wattle framework. But clay has a problem. It shrinks dramatically as it dries. Pure clay daub would crack into a million pieces as the water evaporated out of it, leaving you with a wall that looked like a dried-up lake bed. Not ideal for keeping the weather out. The solution is to add aggregate and fibre. Mixing sand into your clay reduces the overall shrinkage of the material. The ratio varies depending on your specific clay and sand, but something like 2 parts clay to 1 part sand was common. Too much sand and your daub won't stick together properly. Too little and it cracks like crazy as it dries. Medieval builders knew their local materials well enough to get this ratio right through experience. Fibre reinforcement is what really makes daub work as a structural material. And when we talk about fibre in medieval daub, we're primarily talking about straw and animal dung. Yes, you read that correctly. Dung. Specifically herbivore dung, usually cattle or horse, though sheep dung could work in a pinch. Before you get too squeamish about this, understand that herbivore dung is basically pre-processed plant fibre mixed with a bit of manure. The animal has done you the favour of breaking down tough plant material into shorter fibres that mix beautifully into clay. The straw provided longer fibres, typically chopped into lengths of a few inches, that created a reinforcing matrix throughout the daub. Think of it like the rebar in concrete, except made of dead grass and distributed randomly rather than in organised grids. When the daub dried and wanted to crack, these fibres bridged across the potential crack, holding things together. The more fibre you added up to a point, the more crack-resistant your daub became. Medieval builders would sometimes add so much straw and dung that the finished daub was almost more fibre than clay, creating a material that was remarkably tough and flexible. Other additives made occasional appearances in daub recipes. Lime, if you could afford it, improved durability and water resistance. Animal hair, usually cow or horse hair saved from slaughter, provided additional fine-scale fibre reinforcement. Blood from slaughtered animals sometimes got added because it acted as a binder and helped with water resistance. Plus it was free if you lived near a butcher or did your own animal slaughter, which most people did. Urine, human or animal, was occasionally used in small amounts because it contains urea, which has useful chemical properties for working with clay. Medieval builders weren't precious about their ingredients. The mixing process for daub was labour-intensive and usually fell to whoever was lowest on the construction site hierarchy. You'd typically mix daub in a shallow pit or on a large flat surface where you could work it with your feet. Yes, feet. Stomping around in a mixture of clay, water, straw and dung was standard procedure. It's actually an effective method. Your feet provide consistent, relatively strong pressure that breaks up clumps and works the ingredients together into a homogeneous mass. Plus, it leaves your hands free for adding more ingredients or adjusting the mixture. The consistency you were aiming for was similar to very thick porridge, or more accurately like dense mud that holds its shape when you scoop up a handful. Too wet and it would slump off the wattle panels before it could dry. Too dry and it wouldn't adhere properly or spread smoothly. You couldn't measure water content with instruments. You learned what properly mixed daub felt like in your hands and under your feet, and you adjusted accordingly. The application of daub to wattle panels was done by hand. Literally. You'd grab a double handful of this mud mixture and throw it at the wattle panel, then spread and press it in with your hands, forcing it through the gaps between the weavers so it keyed into the structure. The goal was to get daub on both sides of the wattle and have it squeeze through to bond together in the middle, creating a monolithic wall rather than just a coating on each side. Working the daub into the wattle took significant hand strength and persistence. You're not gently spreading this material like butter on toast. You're forcing thick, sticky mud through narrow gaps, pressing hard enough to make it flow and fill voids while also trying to maintain a reasonably smooth surface finish. Your hands would be covered in mud up past your wrists. Your arms would ache from the repetitive pressing motion. Medieval daubers developed impressive forearm strength and probably could have won any arm wrestling competition you cared to name. The typical thickness of a daub wall was about 2 to 3 inches on each side of the wattle, giving you a total wall thickness of around 4 to 6 inches once you accounted for the wattle itself. This provided decent thermal mass and insulation, certainly better than having no wall at all. In areas where winter weather was particularly harsh, builders might go thicker, packing on additional layers of daub to create walls 6 or 8 inches thick overall. The additional mass meant more thermal storage capacity and better wind resistance. The surface finish of daub walls varied by the skill of the applicator and the intended status of the building. For a basic cottage, you might leave the surface relatively rough. As long as it was weatherproof, who cared about aesthetics? But for higher status buildings, daubers would take time to smooth and finish the surface, sometimes using wooden floats or even their hands dipped in water to create a more refined surface. Some buildings show evidence of decorative patterns pressed into the wet daub, creating textures that were both aesthetic and functional. The patterns helped key subsequent coats if you were doing multiple layers. The drying process was critical and couldn't be rushed. Daub needs to dry slowly and evenly to minimize cracking. If it dries too fast, say in hot sun or strong wind, the surface dries first and pulls away from the still wet interior, creating stress cracks. If it's subjected to rain before it's dried sufficiently, it can slump or wash away entirely. Medieval builders had to time their daubing carefully, ideally doing it in mild, dry weather, and then protecting the fresh daub from extremes while it cured. The drying time for daub varied enormously based on weather, wall thickness, and daub composition, but we're talking weeks, not days. A reasonably thick daub wall might need a month or more to fully cure. During this period, the building was vulnerable. You'd sometimes see temporary thatch or boards propped over fresh daub to protect it from rain, while still allowing air circulation for drying. It was a delicate balance. Protect the daub, but don't seal it in so much that moisture can't escape. As daub dried, some cracking was inevitable. Clay shrinks. That's just physics. But properly formulated daub with adequate fibre reinforcement would develop fine hairline cracks rather than major structural splits. These small cracks could be filled in with a thin coat of lime wash or additional daub smoothed over the surface. In fact, daub walls were understood to be living systems that needed periodic maintenance. You'd inspect your walls regularly and patch any developing cracks before they could worsen. This ongoing maintenance was just part of building ownership. The weather resistance of daub walls is actually better than you might expect, though it's not infinite. The clay surface, once dried, is reasonably water resistant in the sense that light rain will run off rather than immediately soaking in. But sustained rain, especially wind-driven rain, will gradually soften daub and can eventually erode it if the wall isn't protected. This is why medieval buildings almost always had significant roof overhangs. Keeping rain off the daub walls was critical to their longevity. Surface treatments helped extend daub wall life. Lime wash, a thin coating of lime mixed with water, was commonly applied to exterior daub. Lime is slightly water-resistant when cured and also has antimicrobial properties that discourage mold and algae growth. It gave walls that characteristic white appearance you see in preserved medieval buildings, though medieval folks probably also appreciated that the white surface reflected light and made interiors brighter. Multiple coats of lime wash, reapplied regularly, could significantly extend the life of daub walls. This was more elaborate and expensive than simple lime wash, but provided additional protection. The lime plaster would take the weather damage, gradually eroding over years, but the underlying daub remained protected. It was a maintenance system that acknowledged the reality of building in a rainy climate. Protection was ongoing, not permanent. Interior daub walls typically received less aggressive treatment because they weren't exposed to weather. A simple smoothing of the surface was often sufficient. Some buildings show evidence of interior lime wash, which served multiple purposes. It brightened the space, sealed the surface against dust and debris shedding, and provided a smooth finish that was easier to keep clean than raw daub. The thermal properties of wattle and daub walls are genuinely impressive for what's essentially stick and mud construction. The mass of the daub provides thermal storage. It absorbs heat slowly during the day and releases it slowly at night, helping moderate interior temperature swings. The fiber content creates tiny air pockets throughout the material, providing insulation value. The combination isn't as effective as modern insulation materials, obviously, but it's far better than having no wall at all, or just a single thickness of wood. Wind-block wattle and daub, when properly applied, is essentially airtight. Wind can howl outside all it wants, but it's not coming through your daub wall. This was crucial in medieval England, where wind chill was a constant winter concern. The difference between a building with proper wattle and daub walls and one with poorly sealed walls was literally the difference between comfortable and miserable, sometimes between survival and death. The acoustic properties are worth mentioning too, even though medieval people probably didn't think about it explicitly. Daub is dense enough to provide decent sound dampening. You're not getting recording studio level sound isolation, but normal conversation in one room isn't easily heard in the next room. This mattered for privacy in crowded medieval households where multiple families or generations might be living under one roof. Having walls that provided at least some acoustic separation made life more bearable. Fire resistance of daub is one of those interesting paradoxes. The material itself is basically unflammable. It's mud. Mud doesn't burn, but the wattle framework inside it is wood, which definitely burns. So a wattle and daub wall will resist fire better than a pure wood wall, but if exposed to sustained high heat, the daub can crack and fall away, exposing the wattle to burn. In practice, most medieval structure fires started in the thatch roof rather than the walls, so the fire resistance of daub was somewhat academic. By the time the roof was fully involved in flames, the whole building was doomed regardless of wall composition. Repairs to wattle and daub were straightforward, which was crucial for buildings that might need to last generations. As long as the underlying wattle remained intact, the repair would bond to the existing daub and restore the wall's integrity. More extensive damage might require replacing sections of wattle, which was more involved but still within the capabilities of a competent handyman. The repairability of wattle and daub meant buildings weren't throwaway items. They could be maintained indefinitely with reasonable effort. The evidence of repairs is visible in archaeological examinations of medieval buildings. You can see patches where different batches of daub with slightly different compositions were applied years or decades apart. You can find sections where wattle was replaced, and the daubing technique is noticeably different, suggesting a different worker did the repair. These patches and repairs are like archaeological records of the building's lifetime, documenting the ongoing maintenance that kept these structures functional for centuries. Regional variations in wattle and daub technique are fascinating and tell you a lot about local conditions and materials. In areas with heavy clay soils, the daub might have less clay content and more sand to prevent excessive shrinkage. In sandy areas, the daub would be clay-heavy to provide adequate binding. Coastal regions sometimes use seaweed as a fibre reinforcement because it was abundant and once dried, quite tough. Some areas incorporated crushed chalk or shell into the daub mix, which improved durability and added insulation value. The aesthetic possibilities of wattle and daub were more extensive than you might expect. Decorative patterning could be impressed into wet daub, geometric designs, religious symbols, or just attractive textures. Some buildings featured contrasting daub colours achieved by using different clay sources with natural iron content that fired to different hues. Wealthy patrons occasionally had their daub tinted with expensive pigments to create colourful exteriors, though this was rare and definitely a status symbol rather than a practical necessity. The social aspects of wattle and daub construction mirror what we've seen with other medieval building techniques. It was accessible, required widely distributed skills, and benefited from community participation. The material gathering could be done by anyone. Collecting clay, cutting willow, preparing straw all required labour but not specialised expertise. The actual construction did benefit from skill and experience. Weaving tight, even wattle panels and applying daub smoothly took practice, but it wasn't so specialised that only a tiny elite could do it. The gender dynamics of wattle and daub work are worth noting. While most carpentry and heavy timber work was male-dominated, daubing often involved women and children because it didn't require the upper body strength needed for timber framing. Mixing daub by stomping was something anyone could do. Applying it required strength and endurance, but not necessarily male-level muscle power. Archaeological evidence suggests that daubing was one of the more egalitarian aspects of medieval construction, with participation from a broader cross-section of the community than some other building tasks. The efficiency of wattle and daub in terms of material cost is striking. Clay from your local soil, free. Willow or hazel from managed coppices, free or very cheap. Straw left over from grain harvest, free. Dung from the animals everyone owned, extremely free and also unavoidable. The only significant cost was labour, and that was often provided through community mutual aid systems. You could literally build substantial weather-tight walls using materials that cost you nothing, except the effort to gather and process them. This material accessibility had profound implications for medieval housing standards. It meant that even relatively poor families could achieve adequate shelter if they had access to land and community support. The barrier to housing wasn't unavailable materials or prohibitive costs. It was labour and skill, both of which could be shared or learned. This is radically different from modern housing economics, where material costs often dominate and access to shelter is mediated primarily through money. The environmental sustainability of wattle and daub is something modern green building advocates are rediscovering. It's a completely renewable building system. The clay goes back to the earth when the building eventually fails. The wood decomposes. Even the straw and dung are biodegradable. There's no toxic waste, no persistent pollutants, no resource depletion. You can harvest another crop of willow shoots in a few years. The clay pit will refill. The system is genuinely sustainable in a way that modern construction often isn't. The embodied energy in wattle and daub construction is essentially just human labour. There's no industrial processing, no high-temperature kilns, no transportation over long distances. Everything is local and low energy. From a carbon footprint perspective, though medieval builders weren't thinking in those terms, wattle and daub is about as minimal impact as building gets. The energy budget for creating these walls was measured in calories consumed by workers, not in tons of coal or barrels of oil. Modern experimental archaeology has validated the effectiveness of wattle and daub in ways that medieval builders simply knew from experience. Reconstructed medieval buildings using proper wattle and daub techniques have proven to be durable, weather-resistant, and thermally comfortable. Monitoring air infiltration measurements confirm that properly executed wattle and daub is remarkably airtight. The longevity of wattle and daub, when maintained, challenges modern assumptions about primitive building materials. There are buildings in England with original medieval wattle and daub walls still functional after 500 or 600 years. That's not because medieval daub was somehow superior to what we could make today. The chemistry is simple and unchanged. It's because the buildings were maintained. Cracks were filled. Limewash was reapplied. The buildings were cared for as living systems rather than static objects. The failure mode of wattle and daub is actually quite graceful compared to many modern materials. When daub finally fails, usually through sustained water exposure that wasn't addressed, it doesn't suddenly catastrophically collapse. It gradually softens and erodes away, giving you plenty of warning that repairs are needed. The wattle framework remains intact even after the daub is gone, still providing basic weather protection and structural stability. You can completely rebuild the daub on existing wattle, restoring the wall to full functionality. This forgiving failure mode meant that even neglected buildings could often be saved with timely intervention. The modern revival of interest in wattle and daub comes from multiple directions. Preservationists need to understand it to properly maintain historic buildings. Sustainable building advocates see it as a model for low-impact construction. Natural building enthusiasts appreciate its use of raw, unprocessed materials. Experimental archaeologists use it to understand medieval construction techniques. Each group rediscovers what medieval builders knew. This is an elegant, effective solution to the fundamental problem of creating weather-tight walls using locally available resources. Teaching wattle and daub construction today reveals how much tacit knowledge the medieval system required. You can explain the technique clearly in words, but until you've actually woven willow shoots between stakes and felt how the material wants to move, until you've mixed daub with your feet, until the consistency is right, until you've pressed thick mud through wattle with your hands until your forearms burn, you don't really understand it. Medieval builders learned by doing, through apprenticeship and experience. Modern students discover the same thing. This is embodied knowledge that lives in your hands and muscles, not just in your head. The satisfaction of completing a wattle and daub wall is apparently universal across time. Modern builders report feeling accomplishment when they step back and look at a section of wall they've just daubed. Medieval builders probably felt the same satisfaction, though for them it was leavened with the practical reality that this wall was protecting them from freezing to death, which adds a certain urgency to your craftsmanship. So here's the thing about wattle and daub. It looks primitive. Sticks woven into a basket, mud smeared over them, dried in the sun. It sounds like something children might make in a backyard fort. But it's not primitive. It's appropriate technology executed with sophisticated understanding of materials science, structural mechanics, and thermodynamics, even if those concepts weren't formalized into scientific disciplines yet. Medieval builders knew how to make these walls work in their specific environment with their available resources. That's not ignorance. That's expertise. And when your modern building technology is amazing, no question. But it's worth remembering that people were creating effective, durable, comfortable shelter centuries before anyone invented fiberglass insulation or oriented strand board. They did it with willow, clay, straw, and knowledge accumulated over generations. That deserves respect, not condescension. So you've got your sturdy cruck frame, your beautifully woven wattle and daub walls, and a structure that's shaping up to be genuinely habitable. Excellent. There's just one glaring problem remaining. You're still completely open to the sky. Rain falls directly into your house. Snow accumulates on your floor. Birds can theoretically nest in your rafters without even trying. You need a roof, and in medieval England, that roof was almost certainly going to be made of thatch, which is just a fancy way of saying dead grass. Though calling it that undersells the sophistication of what was actually a remarkably complex and effective roofing technology. Thatch has been protecting humans from the weather for thousands of years, which should tell you something about its effectiveness. It's not primitive. It's proven. The basic principle is simple enough. You take bundles of straw or reeds, layer them in overlapping courses like scales on a fish, and create a thick, water-shedding barrier between you and the elements. But as with everything else in medieval construction, the devil is in the details, and those details represent centuries of accumulated knowledge about how to make a roof that actually works, rather than just collapsing into a soggy heap the first time it rains. Let's start with materials, because what you thatch with matters enormously. The two primary options in medieval England were wheat straw and water reed, though other materials made appearances depending on local availability. Each had distinct characteristics and required somewhat different techniques, and medieval thatchers developed strong opinions about which was superior, probably leading to spirited debates in medieval taverns that sound remarkably like modern arguments about whether gas or electric stoves are better. Once you'd threshed your grain, separated the wheat kernels from the stalks, you were left with piles of straw that needed to go somewhere. Some became animal bedding, some got composted, and the best quality stuff became roofing material. This circular economy is actually quite elegant when you think about it. Your food crop produces waste that becomes your shelter material. Nothing goes unused, but not all wheat straw was created equal for thatching purposes. You wanted long stem varieties that hadn't been crushed or broken during harvest. The threshing method mattered too. Traditional flail threshing, where you beat the grain heads with a wooden tool, left the straw largely intact. More aggressive threshing methods that crushed and mangled the stalks produced straw that was useless for roofing. Medieval farmers who wanted good thatch straw had to be careful during harvest and processing, which added labour but resulted in a more valuable product. The quality indicators for thatch straw were things you learned to recognise through experience. The stalks should be intact from root to head, ideally 3 to 4 feet long. They should be relatively straight. Kinked or badly bent straw didn't lay properly in courses. The colour should be golden rather than grey or mouldy, indicating proper drying and storage. The stalks should be flexible enough to bend without snapping, but not so green that they'd rot on the roof. Medieval thatchers could run their hands through a bundle of straw and immediately assess its suitability, the way a textile merchant could judge fabric quality by touch. Water reed was the premium thatching material, and if you had access to it, you were doing well. Reed grows in wetlands, marshes, and along waterways, anywhere that stays consistently wet. England has plenty of such areas, particularly in the eastern counties, and reed harvesting was an established industry throughout the medieval period. Reed has several advantages over straw that made it worth the extra effort to obtain. It's more durable, lasting perhaps 50 to 60 years on a roof compared to 25 to 30 for wheat straw. It's more water resistant due to its natural waxy coating, and it's less attractive to birds and rodents looking for nesting material, which was a constant problem with straw roofs. The harvest season for reed was winter, when the plants had died back and dried naturally. Medieval reed cutters would wade into freezing marshes with specialised tools, long-handled scythes or sickles, and cut the reeds close to the waterline. This was miserable work done in brutal conditions, which partially explains why reed was more expensive than straw. You weren't casually gathering material from your already harvested grain field. You were deliberately going into hostile environments in winter to harvest a specialized product. That cost. Processing reed for thatching involved bundling the cut stems into manageable bundles called bolts, typically about 2 feet around. These bundles were tied tightly and then stored in a dry location to complete their drying process. Reed needed to be completely dry before use. Wet reed on a roof would rot before it had a chance to properly cure. The storage requirements meant you needed space to keep significant quantities of reed under cover for potentially months between harvest and use, which was yet another factor in its higher cost. Other thatching materials made regional appearances based on what was available. In coastal areas, you sometimes see roofs thatched with sedge, which is similar to reed but grows in slightly different conditions. Heather was used in upland areas where it grew abundantly. It made for a rougher-looking roof but was incredibly durable and fire-resistant, which was actually a significant advantage. Some areas used broom, gorse, or even turf for roofing, though these were less common and usually indicated either poverty or specialized building types like animal shelters. The preparation of thatching material was labor-intensive. Straw or reed needed to be sorted with damaged or substandard material culled out. What remained was organized into bundles of consistent size. This standardization was crucial because the thatcher needed to know that each bundle would cover roughly the same area and create consistent thickness. The bundles were typically soaked in water before use, which made the straw or reed more pliable and easier to work with. Medieval thatchers would have a water trough or pond nearby where they'd dunk bundles and let them absorb moisture for a few hours before carrying them up to the roof. Now let's talk about the actual thatching process, which required genuine skill and wasn't something you could fake your way through. A bad thatch job would leak, potentially catastrophically, and you'd know about it the first time substantial rain arrived. Medieval thatchers were respected craftsmen who commanded decent wages, and for good reason. They were the last line of defense between you and hypothermia. The roof pitch, the angle of the roof, was critical to thatch performance, and this is where you see medieval builders' understanding of water physics. A thatch roof needed to be steep, typically 45 to 50 degrees or more from horizontal. This wasn't aesthetic choice, it was functional necessity. Water needs to run off the roof faster than it can penetrate through the thatch layers. On a shallow pitched roof, water sits on the surface too long and eventually finds its way through. The steepness requirement had structural implications. Remember those crux frames we discussed? The angle of the crux partially determined your roof pitch. Builders designing structures to be thatched needed to ensure their framing would support an adequately steep roof. Too steep and you'd use excessive materials and create weird proportions, though honestly, thatch roofs are hard to make too steep from a functional standpoint. Steeper is generally better for water shedding. The roof's horizontal purlins spanning between the crux frames or rafters, typically spaced about 12 to 18 inches apart. Sometimes there would be lighter battens running parallel to the roof pitch for additional support. The goal was a framework that would hold the weight of the thatch, which was substantial as we'll discuss, while providing attachment points for securing the thatch bundles. Thatching started at the bottom of the roof and worked upward, which is logical when you think about water flow. The bottom course of thatch was installed first, typically extending beyond the wall line to create an overhang that directed water away from the walls. Each bundle of straw or reed was positioned horizontally along the roof, with the cut ends pointing down and the naturally tapered ends pointing up. This orientation is crucial. Water running down the roof encounters the smooth, overlapping straw surfaces rather than the cut ends where it could penetrate. The attachment method for thatch varied by region and builder preference, but the most common technique involved using pointed wooden stakes or metal hooks to pin the bundles to the roof structure, then securing everything with twisted straw or hazel withies. The goal was to hold each bundle firmly in place while still allowing the bundles to overlap and interlock with their neighbours. The next course of thatch was laid above the first, overlapping by roughly half the length of a bundle. So if your bundles were 2 feet long, the overlap would be about 12 inches. This overlapping created the multi-layered structure that gave thatch its weather resistance. Water hitting the roof surface would run down the top layer, hit the overlap and continue down the next layer. By the time water had travelled through multiple layers, it had also travelled horizontally along the roof for several feet, and had ideally run off the edge before penetrating all the way through to the interior. The thickness of a finished thatch roof was impressive, typically 12 inches minimum, often 18 to 24 inches for quality work. In areas with harsh weather, thatch roofs could be even thicker, sometimes reaching 30 inches or more of layered straw. This wasn't excessive or wasteful. It was necessary. Each layer contributed to weather resistance, insulation value, and structural integrity. A thin thatch roof was a leaky thatch roof. Medieval builders understood that adequate thickness was non-negotiable. Working your way up the roof, the thatcher would maintain consistent overlap and thickness, periodically checking that the surface was smooth and even. Lumps or depressions in the thatch surface would collect water rather than shedding it, creating weak points where leaks could develop. Good thatchers developed an eye for these problems and would redistribute material, adding extra here or removing some there to maintain proper water flow characteristics. It was as much art as craft. You couldn't just mechanically apply bundles and hope for the best. The ridge, the peak where the two sides of the roof met, required special treatment. You couldn't just leave a gap at the top where the two roof surfaces came together. That would be, well, problematic for obvious reasons. The ridge treatment involved creating a capping structure that covered the joint and was secured in ways that could withstand wind trying to peel it off. One common method was to lay bundles perpendicular to the roof slope, straddling the ridge, and secure them with stakes and lashings. Another was to create decorative patterns with tightly packed straw that also served to seal the ridge. The aesthetic possibilities of ridge decoration meant that thatchers could show off their skill while also doing necessary structural work. You see surviving examples and historical depictions of ridges with elaborate geometric patterns, crosses, birds, or other designs worked into the thatch. This wasn't frivolous decoration. The tight packing and intricate work required to create these patterns resulted in a ridge that was extremely weather-resistant. Making it look good was a bonus on top of making it functional. The eaves, the bottom edge of the roof, also needed careful attention. This was where water would ultimately run off, and it had to be neat and straight so water would drip away from the building rather than running back along the underside of the thatch. Thatchers would trim the eaves with specialized tools, creating a clean, even edge. The trimmed edge was often quite thick. Remember, you've got 12 to 24 inches of thatch thickness, so the eaves presented a substantial face. Some thatchers would create decorative edge patterns, though functionality remained the priority. The time required to thatch a roof depended on size, complexity, and crew size, but we're talking about days or weeks of work, not hours. A small cottage might take a skilled thatcher and one or two helpers about a week of steady work. A larger building could take several weeks. The medieval approach to construction timelines was generally more relaxed than modern expectations. Work proceeded as weather allowed, materials were available, and workers could be spared from other tasks. Rushing a thatch job was counterproductive because mistakes meant leaks, and leaks meant you'd have to redo the work anyway. The weight of a completed thatch roof is something modern people often underestimate. We're talking about significant mass. A well-thatched roof could easily add several tons of weight to a structure. Wheat straw is lighter than reed, perhaps 30 to 40 pounds per cubic metre compared to 60 to 70 for reed. But when you're covering a roof with 12 inches of material, it adds up fast. This loading had to be accounted for in the building's structural design. Your cruck frames and purlins needed to be sized to handle not just the dead load of the thatch, but also additional snow load in winter. The snow load consideration was serious in medieval England. A heavy snow on top of an already loaded thatch roof could stress the structure significantly. The steep pitch that was necessary for water shedding helped here too. Snow would generally slide off a properly pitched thatch roof rather than accumulating indefinitely. But during heavy snowfall, especially if it was wet, sticky snow, the load could be considerable. There are medieval records of roof failures during severe winters, usually attributed to snow accumulation exceeding the structure's capacity. The insulation value of thatch is genuinely impressive and often surprises people used to modern materials. All those layers of straw or reed create countless tiny air pockets, and trapped air is an excellent insulator. The thermal resistance of 12 inches of thatch is roughly equivalent to 3 to 4 inches of modern fiberglass insulation. That's not as good as contemporary insulation, but it's far better than nothing. And remember, medieval folks didn't have fiberglass as an alternative. They had thatch, and thatch did a remarkable job of keeping interiors warm in winter and cool in summer. The summer cooling effect is something we don't often think about in the context of medieval England. We're so focused on surviving winter that we forget summer existed. But thatch roofs in summer provided significant cooling through two mechanisms. First, the insulation value worked both ways. It slowed heat transfer from the hot roof surface into the building. Second, thatch breathes. Air can move through the material, allowing hot air to escape from the building while cooler air circulates in. Modern vapor barriers and synthetic roofing don't allow this breathability, which is why attics in modern houses can become dangerously hot in summer. The moisture management in thatch roofs is counterintuitive until you understand the principles. You'd think that organic material like straw or reed would rot quickly when constantly exposed to rain, and it would if it stayed wet. But thatch works because it dries rapidly. Water hits the surface and runs off immediately due to the steep pitch. The small amount that does penetrate the outer layers is absorbed by the straw, but then air circulation through the thatch allows it to evaporate quickly. The material cycles between wet and dry constantly, never staying saturated long enough for rot to establish. This cycling is why thatch in shaded areas or on low-pitch roofs fails faster. It can't dry properly between rain events. Medieval builders understood this empirically even if they didn't know about fungal growth requirements. They knew that thatch in sun performed better than thatch in shade. They knew steep roofs lasted longer than shallow ones. They incorporated this knowledge into their building designs, positioning structures and choosing roof pitches based on accumulated experience about what worked. The lifespan of a thatch roof varied enormously based on material quality, installation skill, local climate, and maintenance. A well-made wheat straw roof in a favourable location might last 25 to 30 years. A poorly made one might fail in 10. Reed roofs could last 40 to 60 years with good maintenance. The roof didn't fail all at once. It deteriorated gradually, with the outermost layers breaking down first while the interior layers remained intact. This gradual failure gave warning that repairs or replacement were needed. Maintenance was crucial and ongoing. Medieval homeowners would inspect their thatch regularly, looking for areas where the material was thinning, where birds had pulled out straw for nesting, where moss was growing, or where any other problems were developing. Small repairs, pushing loose straw back into place, adding a few new bundles to thin spots, could be done by the homeowner. Larger repairs required calling in a thatcher, but catching problems early meant repairs were cheaper than waiting for catastrophic failure. The fire risk of thatch was real and significant, and medieval people were acutely aware of it. A thatch roof is essentially a pile of dried grass sitting on top of your house. If it catches fire, it burns enthusiastically and your entire building is probably doomed. Once a thatch roof was well involved in fire, there was essentially no saving it. You evacuated and hoped the walls would survive. Medieval building regulations in towns often addressed thatch fire risk by requiring tile or slate roofs within city limits, or at least in areas of dense construction where one burning building could easily ignite its neighbours. Thatch remained common in rural areas where buildings were more dispersed and the fire risk to neighbours was reduced. The economic reality was that thatch was vastly cheaper than tile or slate, so most people accepted the fire risk because the alternative was unaffordable. Fire prevention strategies for thatch roofs included keeping the roof surface clean. Dead leaves and debris were fire hazards. Chimneys needed to be properly designed with enough height and spark-arresting features to prevent embers from landing on the roof. Some people applied clay or lime wash to the underside of their thatch as a fire retardant, though effectiveness was questionable. Really, the best defense against thatch fires was vigilance and good chimney maintenance combined with luck. Regional variations in thatching technique are fascinating and often reflect adaptations to local conditions. In coastal areas with high winds, thatchers used additional securing methods, more stakes, tighter lashings, sometimes even stone weights suspended from the roof edges to hold everything down. In areas with heavy snow, steeper pitches and thicker thatch were standard. Wetter regions might favour reed over straw for its superior durability. Drier regions could get away with thinner thatch and shallower pitches. The decorative traditions that developed around thatching show that even with functional material and serious purpose, humans can't resist making things beautiful. Beyond ridge decoration, some regions developed traditions of creating patterns in the thatch surface itself, geometric designs, dates, initials of the builder or owner, religious symbols. These weren't just aesthetic choices. The tight, careful work required to create patterns resulted in better quality, longer-lasting thatch. Making it pretty and making it functional went hand in hand. The social status of thatchers in medieval society was respectable but not elite. Thatching was often a seasonal occupation. You did most of your work in late summer and fall after harvest when straw was available, and before winter weather made roof work miserable. During winter and spring, thatchers might work at other trades or do repair work. This seasonal rhythm fit naturally into the agricultural calendar that governed medieval life. The training of thatchers followed the standard medieval apprenticeship model. A young person would apprentice to a master thatcher for several years, learning the craft through observation and gradually increasing responsibility. You'd start with preparation work, sorting straw, making bundles, mixing the soaking water. Then you'd assist on roofs, handing up materials and doing basic tasks. Eventually, after several years, you'd be competent enough to work independently and perhaps take on your own apprentices. The tools of the thatcher were surprisingly minimal. A wooden rake for spreading and positioning straw, metal hooks or stakes for securing bundles, shears or a sharp knife for trimming, a wooden bat or paddle for packing down thatch and creating a smooth surface, a needle-like tool for threading lashing cords through the thatch. That was basically it, a toolkit that fit in a small bag. The skill was in the user, not the tools. A master thatcher with basic tools would create a better roof than a novice with the finest equipment available. The economics of thatching made it accessible to most of the population, which had enormous implications for housing standards. Compared to tile or slate, thatch was cheap. The material was essentially free if you grew grain or had access to reed beds. The labour cost was the main expense, and even that was manageable. A typical roof might cost the equivalent of a month's wages for a labourer, which was significant but not impossible to save toward. This meant that even relatively poor families could afford weathertight roofs, which is a bigger deal than it might sound. Adequate shelter is foundational to everything else in life. The decline of thatching in later centuries wasn't because the technology failed or became obsolete. It was a combination of factors. The fire risk became less acceptable as insurance and firefighting capabilities improved. Tile and slate became more affordable as production scaled up. And frankly, thatch came to be seen as old-fashioned and rustic. By the 19th century, a thatch roof marked you as either poor or nostalgically traditional. The technology was fine. Social preferences changed. Modern thatch revivals are driven by different concerns: historic preservation, aesthetic preference, environmental consciousness. Contemporary thatchers using traditional techniques create roofs that perform as well as they did in medieval times, which is to say, very well if properly designed and maintained. The principles haven't changed. Steep pitch, adequate thickness, quality materials, skilled installation. The environmental sustainability of thatch is something medieval people didn't think about explicitly, because everything was sustainable by default. They didn't have unsustainable alternatives. But from a modern perspective, thatch is impressively eco-friendly. It's made from annually renewable crops. It requires minimal processing, just cutting and drying. It's fully biodegradable. At end of life, old thatch can be composted or used as mulch. The carbon footprint is essentially zero beyond the human labour involved. Compare that to asphalt shingles derived from petroleum products, and you see why some modern builders are reconsidering traditional materials. The craft knowledge embedded in medieval thatching represents generations of accumulated wisdom. When to harvest, how to prepare materials, how to layer for maximum weather resistance, how to handle difficult roof geometries, how to predict and prevent common failure modes. None of this was written down in accessible form. It lived in the hands and minds of working thatchers, passed from master to apprentice in an unbroken chain going back centuries. Some of that knowledge was lost as thatching declined, but remarkably, much has been preserved by the small community of traditional thatchers who maintained their craft even when it fell out of fashion. The modern study of medieval thatch involves multiple approaches. Archaeological examination of surviving thatch buildings shows how techniques evolved over time. Experimental archaeology, actually thatching roofs using medieval methods, tests our understanding of the process and reveals details that can't be learned from examination alone. Historic documents occasionally mention thatching practices or costs. Together, these sources paint a detailed picture of a sophisticated roofing technology that served most of England's population for centuries. The simple fact that many medieval thatched buildings still exist and remain weathertight after 500, 600, 700 years is powerful testament to the effectiveness of the technology. These roofs have survived centuries of English weather, rain, snow, wind, sun, and continue functioning. They've been maintained certainly, but maintenance is expected for any building system. The point is that the fundamental technology works. Medieval thatchers knew what they were doing. So when you're tucked under your modern roof, asphalt shingles maybe, or metal panels with fiberglass insulation and plywood sheathing and all the products of industrial manufacturing, spare a thought for medieval folks sleeping under layers of straw or reed, 12 inches thick, laid by skilled hands using techniques refined over generations. Their roof kept them just as dry as yours keeps you, and it did so using nothing but grass and craftsmanship. That's not primitive. That's sophisticated, appropriate technology that solved a fundamental human need with remarkable effectiveness. And honestly, There's something deeply satisfying about the idea that the same material that fed you, wheat straw from your grain harvest, also sheltered you from the elements. Medieval life had a circularity and integration that modern life often lacks. Your food, your shelter, your fuel, all came from your land and your labour. It was harder in many ways, sure, but it was also more comprehensible. You could understand your entire material life, from seed to bread to roof to firewood to compost. Everything connected. Everything made sense. That's worth appreciating, even from the comfort of your modern, non-thatched home. Now we've covered how medieval English folks built their structures, wove their walls, and thatched their roofs. We've talked about all these clever techniques for keeping warm and dry using nothing but local materials and accumulated knowledge. But there's one heat source we haven't discussed yet, and it's probably going to make modern people deeply uncomfortable. Ready? Here it is, livestock. As in cows, pigs, sheep and chickens living inside your house with you. Not in a barn, not in a separate structure. Inside. Where you sleep. Where you eat. Where you do everything else humans do in their homes. I can practically hear you recoiling from your screen right now. This was deliberate practical engineering that solved multiple problems simultaneously. Medieval peasants weren't stupid. They weren't keeping livestock indoors because they enjoyed the ambience of cow manure in their living space, though they probably got used to it. They were doing it because it made excellent sense given their circumstances, their resources, and their survival needs. And honestly, once you understand the reasoning, it's hard to argue with the logic even if you personally wouldn't want to try it. The fundamental principle here is straightforward. Animals generate heat. Specifically, large mammals like cows generate significant amounts of heat as a byproduct of their metabolism. A single cow produces roughly the same heat output as a small space heater running constantly, somewhere around 1500 to 2000 watts of thermal energy, just from existing and doing normal cow things like breathing, digesting, and maintaining body temperature. That's not trivial. That's a meaningful heat source that could make the difference between a barely survivable house and a genuinely comfortable one. Let's run some numbers because the thermodynamics here are actually impressive. A typical medieval cottage might house a family of 4 to 6 people, plus perhaps 2 or 3 cows, a pig, some sheep, and chickens. Each human generates about 100 watts of heat at rest, more when active. The cows are contributing maybe 3 to 4,000 watts combined. The pig adds another 3 to 500. The sheep, maybe 2 to 300 total. The chickens are basically negligible from a heating standpoint, but they're in there too. Add it all up and you've got a living space being heated by roughly 5 to 6,000 watts of biological furnaces, operating 24 hours a day, 7 days a week, requiring no fuel beyond whatever the animals were eating anyway. Compare that to what you'd need from a wood fire to heat the same space. A small cooking fire might produce 2 to 3,000 watts of heat, but you need to constantly feed it with wood that someone had to gather and cut and store. The fire goes out if you don't maintain it. The animals? They just keep generating heat automatically, night and day, as long as they're fed. From a pure efficiency standpoint, animals as supplementary heating made perfect sense. They were assets you already owned for other reasons: milk, meat, wool, eggs, and their heat production was a bonus feature you'd be foolish not to exploit. Now, the layout of these shared human-animal spaces followed certain logical patterns that show up repeatedly in archaeological and standing medieval buildings. The typical arrangement was what's sometimes called a longhouse design, though that term gets used loosely for various building types. The basic idea was a single rectangular structure divided into zones. One end would be primarily for human habitation. This is where the hearth was located, where people slept, where food was prepared. The other end was the byre or shippon, the area designated for livestock. The two zones weren't completely separated. There might be a partial partition or just a few posts marking the boundary, but there was definitely a conceptual division between people space and animal space. This division was more aspirational than absolute. Animals, particularly when you're dealing with a dozen or more of them in close quarters, don't respect boundaries all that carefully. Chickens especially have no concept of staying in their designated area. They'd wander throughout the entire structure, which is actually fine because chickens are small and relatively clean as far as livestock go. The larger animals, cows, pigs, sheep, would mostly stay in their end of the building, but there was definitely some intermingling, particularly around the margins. The terminology here is worth noting because it shows up in historical documents and architectural descriptions. The beast corner or beast end referred to the livestock area. The hall or dwelling end was the human space. Sometimes you see references to a cross passage, a corridor running perpendicular to the main axis of the building, separating the two zones and providing separate entrances for humans and animals. This architectural feature shows up often enough that it's clearly a recognized design element rather than random variation. The floor levels in these shared structures were usually differentiated. The human living area would be slightly elevated, maybe just a few inches, maybe as much as a foot above the animal area. This height difference served multiple practical purposes. First, it provided some psychological separation. You're literally living on a higher plane than your livestock, which probably felt important from a dignity standpoint. Second, and more practically, it meant that any liquid waste from the animals, and there would be liquid waste constantly, would flow away from the human living area rather than toward it. Gravity is your friend when dealing with bovine urine. The drainage situation deserves more attention because it was actually quite sophisticated when done properly. The animal end of the building would have a slightly sloped floor, typically dirt or packed clay, angled toward the entrance or toward a drainage channel. Some buildings had stone-lined gutters running down the middle of the byre, collecting animal waste and directing it out of the structure. The really elaborate setups had external drainage leading to a midden or compost heap, creating a waste management system that was surprisingly advanced for what we think of as primitive buildings. The practical realities of living with large animals indoors are exactly as challenging as you'd imagine, and medieval people dealt with this through a combination of management strategies that required constant attention. Bedding was critical. You needed thick layers of straw or rushes on the floor of the animal area to absorb moisture and waste. This bedding required regular refreshing. This isn't as disgusting as it sounds. The composting process generates heat, adding to your overall warmth, and as long as you keep adding fresh material on top, the surface stays relatively dry and doesn't smell too offensive. The mucking out schedule varied by season and by how many animals you were housing and how much space. In deep winter, you might let the bedding accumulate for weeks or even months, taking advantage of that composting heat and minimizing the amount of time you needed to have doors open to remove waste. In spring, you'd do a major clean-out, hauling all that accumulated, partially composted bedding out to your fields where it became excellent fertilizer. This cycle, accumulate bedding and waste all winter, spread it on fields in spring, was standard agricultural practice and shows how integrated everything was in medieval farming. Your animals' winter housing literally improved your summer crops. The smell is something we need to address because modern people fixate on it, and yes, obviously it smelled. These buildings absolutely had a distinctive odour that combined animal musk, manure, straw, wood smoke, cooking food, unwashed humans, and whatever else was going on. But here's the thing, medieval people's olfactory environment was completely different from ours. They weren't living in Lysol-scented, HEPA-filtered modernity and then suddenly thrust into a barn. They'd lived with these smells their entire lives. Their baseline for normal included animal odours because animals were everywhere in medieval life. The smell of cows or pigs in your house wasn't remarkable. It was just background. Also, and this is important, medieval people did make efforts to manage odours even if they couldn't eliminate them. Smoke from the hearth fire actually helped. Smoke has antibacterial properties and tends to mask other odours. Fresh rushes or herbs strewn on the floor in the human living area provided pleasant smells that competed with less pleasant ones. Regular addition of fresh straw in the animal area helped. Opening doors and windows when weather permitted provided ventilation. Nobody was celebrating the smell of livestock, but they had strategies for making it tolerable. The health implications of living with animals are complex and have been debated by historians and epidemiologists. On one hand, yes, zoonotic diseases that jump between animals and humans, were definitely a risk. You're in close contact with livestock, breathing the same air, dealing with their waste, touching them regularly. That creates transmission opportunities for various pathogens. Some medieval disease outbreaks probably originated or spread through these close human-animal interactions. On the other hand, the constant low-level exposure to various microorganisms probably strengthened immune systems in ways that made medieval people more resistant to certain infections. This is the hygiene hypothesis in action. Modest exposure to dirt and germs in childhood helps develop robust immune responses. The evidence is mixed and interpreting it is tricky, but the point is that living with animals wasn't automatically a health disaster. The practical benefits beyond heating were substantial and shouldn't be overlooked. Having your livestock inside meant they were protected from predators. Wolves still existed in medieval England, and foxes are always a threat to chickens. They were protected from theft. which was a real concern in a society where a cow might represent a substantial portion of a family's wealth. You could check on sick or pregnant animals throughout the night without going outside in the cold. You had immediate access to fresh milk from the cows without having to trek to a separate barn in winter weather. These convenience factors added up to significant quality of life improvements. The security aspect particularly mattered. A cow might be worth as much as a year's income for a peasant family. Losing it to theft or predation could be economically devastating. Having the animal sleeping inside with you meant that anyone trying to steal it would have to break into your house and somehow get past a family of sleeping humans, which is considerably harder than just sneaking up to an isolated barn. The livestock weren't just assets, they were capital, and keeping them close was sound financial management. The winter survival equation for livestock is worth understanding because it shows why indoor housing made sense from the animal's perspective too. Cows, pigs, and sheep can survive cold temperatures, but they need to eat more to maintain body heat, and they're more likely to get sick or die if they're also wet, windy, and stressed. A sheltered animal is a healthier animal that requires less food to maintain condition. For medieval farmers operating on thin margins where animal feed was limited, anything that reduced feed requirements while keeping animals healthy was worth doing. The caloric math worked out favourably. Yes, you had to share your limited space with livestock. Yes, you dealt with the smell and mess. But in return, your animals stayed healthier on less feed, produced more milk, and were more likely to survive winter. The heat they provided reduced your wood gathering requirements. The waste they produced improved your fields. It was a system with multiple interlocking benefits that justified the very real drawbacks. The social status implications of shared housing with animals are fascinating. Richer households didn't do this. Once you could afford separate structures, a house for humans, a barn for animals, you built them and moved the livestock out. Keeping animals inside your house was a marker of poverty or at least modest means. But it wasn't shameful exactly, just normal for most of the population. The majority of medieval English peasants lived this way for most of the medieval period. It was standard practice, not an embarrassing secret. The regional variations in human-livestock cohabitation reflect different agricultural systems and building traditions. In areas focused on cattle raising, you'd see larger, more elaborate byres attached to houses. In sheep-heavy regions, the arrangements might be different because sheep have different housing needs than cattle. Pig keeping created its own challenges because pigs are messier and more destructive than other livestock, so they'd sometimes be housed in partially separate structures or in particularly robust sections of the main building. The specific arrangements varied, but the basic principle, animals and humans sharing space for mutual benefit, showed up across most of medieval England. The decline of this practice tracks with economic development and changing agricultural systems. As the medieval period progressed into the early modern period, more people could afford separate buildings. Agricultural improvements meant better winter feed availability, reducing the critical importance of keeping animals inside for their survival. Social attitudes shifted. Having animals in your house came to be seen as backwards and lower class rather than normal and practical. By the 16th and 17th centuries, the longhouse tradition was fading in most of England, though it persisted longer in remote or economically marginal areas. The archaeological evidence for shared human-animal housing is extensive and sometimes quite detailed. Excavations of medieval buildings reveal distinct differences between the two ends. The human end has hearths, where patterns consistent with food preparation and sleeping, finer artifacts like pottery and tools. The animal end has different floor composition, drainage features, sometimes stone-lined stalls or feeding troughs. The spatial organisation is usually quite clear once you know what you're looking at. Some buildings show evidence of evolution over time. A structure might start as a straightforward shared space, then later have a more substantial partition added, then eventually have the byre section converted to other uses once livestock were moved to a separate barn. These modifications tell stories of families' economic trajectories, starting out poor and building up to the point where they could afford proper animal housing. The archaeology captures these personal economic histories in ways that written records rarely do. The modern experimental archaeology projects that have recreated medieval living conditions, including the animal cohabitation aspect, provide valuable insights into what this was actually like. Groups have done winter stays in reconstructed medieval buildings with livestock present, monitoring temperatures, documenting daily management requirements, and generally experiencing the reality rather than just theorizing about it. It's workable. The animals provide genuine heating benefit. The management tasks become routine. You adapt. The temperature measurements from these experiments are particularly interesting. Without animals present, A medieval building with just a small hearth fire might maintain interior temperatures in the 40s or low 50s Fahrenheit on a cold night. Survivable, but not comfortable. Add 4 or 5 cows to the equation, and interior temperatures rise into the 50s or even low 60s, which is genuinely comfortable, especially if you're under blankets sleeping. That 10 to 15 degree difference isn't trivial. It's the difference between miserable and manageable. The behavioral dynamics between humans and animals in shared space apparently required some training on both sides. The animals had to learn where they were supposed to be and what behaviors were acceptable. You couldn't chicken. Medieval farmers trained their animals through consistent reinforcement, correcting unwanted behaviors, rewarding compliance with treats or positive attention. It wasn't formal training like you'd see with modern working animals, but there were definitely behavioral expectations that animals learned to meet. The humans also had to adapt their behaviors. You learned to be aware of where the animals were to avoid accidentally stepping on a sleeping pig in the dark. You developed the habit of closing doors and barriers to keep animals in their designated areas. You got used to the constant background noises, animals shifting around, making their various sounds, occasionally having disputes that needed to be broken up. It became second nature, the way modern people tune out traffic noise or adapt to living in apartments with neighbours above and below. The nighttime dynamics are particularly interesting to consider. Medieval people typically slept in shorter segments. There's good historical evidence for a first sleep and second sleep pattern, with a period of wakefulness in between. During that wakeful period, when people might get up to tend the fire, check on children, or do various quiet tasks, they'd also naturally check on the animals. Make sure nobody was in distress, that the bedding was adequate, that everything was peaceful. The animals became part of the household's rhythms in ways that are hard for modern people to fully appreciate. The emotional relationships between medieval people and their livestock probably varied widely by individual personality and circumstances. Some people undoubtedly viewed their animals purely as economic assets, milk producers, meat on the hoof, wool factories. Others probably developed genuine affection for individual animals, gave them names, recognized their personalities. When you're living in intimate proximity with a cow for years, milking her twice a day, sleeping in the same building, it would be strange not to develop some kind of relationship beyond pure economic calculation. The children growing up in these environments learned animal husbandry from birth. They'd be playing around livestock from their earliest years, learning to read animal behavior, understanding the daily rhythms of feeding and milking and mucking out. This early education was valuable. Competent animal management was a crucial life skill for most medieval people, and starting that education in infancy through constant exposure made sense. Modern children learn to read and use computers from young ages. Medieval children learn to understand and work with livestock. The documentation of these living arrangements in medieval sources is frustratingly sparse, because it was so normal nobody thought to write about it in detail. You see occasional mentions in legal documents, disputes over shared walls in buildings where one party's animals were causing problems for the neighbour, for instance. You see it implied in architectural descriptions, references to buyers attached to houses, mentions of the beast end of buildings. Building regulations sometimes address it, usually in the context of fire safety or urban planning, but detailed descriptions of how it actually worked. Those are rare because contemporary writers didn't think it needed explaining. The transition to separate housing for animals was gradual and uneven. Wealthy households made the change earlier. Rural areas maintained the practice longer, and in some remote locations it persisted into the 18th or even 19th centuries. The drivers for change were economic, being able to afford separate buildings, and social, wanting to live in ways that marked you as respectable and modern, rather than backwards and poor. The loss of this tradition represents a significant change in human-animal relationships. For most of human history, people lived in close proximity to their livestock. The agricultural revolution that began in the Neolithic created these relationships that persisted for thousands of years. The medieval period represents perhaps the peak of this tradition in Europe. Sophisticated agricultural societies where humans and animals shared space as a deliberate, beneficial arrangement. The subsequent separation of human and animal spaces in the modern era has advantages in terms of hygiene and disease control, but it also represents a distancing from the realities of where our food comes from. The modern visitor to a preserved medieval building that once housed people and animals together usually has a strong reaction. The spaces feel small, the ceilings low, the thought of animals living there with humans seems impossible. But you have to remember that medieval people weren't modern people who'd been thrown back in time. They grew up in these spaces. This was their normal. And normal is powerful. It shapes what seems possible, reasonable, even desirable. What strikes us as impossible would have struck them as obviously sensible given their circumstances. The comparison to modern practices is interesting. We still house pets, dogs, cats, inside our homes, sharing our living space with animals. We've just drawn the line at different species based on size and hygiene considerations. A medieval peasant might find our practice of letting dogs sleep in our beds while finding the idea of a cow in the next room horrifying to be completely backwards. They'd point, it's all about what you're used to and what serves your needs. The environmental control aspects of shared housing are worth revisiting because they tie into our earlier discussions about thermal management. We've talked about earth berming, about thick thatch roofs, about small windows and heavy doors, all strategies for controlling heat loss. Animals inside the building are the final piece of that puzzle, the biological heat source that makes all those other strategies effective. Without the animals are the elegant solution that makes the whole system work. The waste-to-resource pipeline in medieval agriculture heavily featured these indoor-housed animals. The bedding and manure that accumulated over winter became the fertilizer that improved summer crops, which produced the grain that fed both humans and animals, which produced the straw that became bedding and roofing material. Everything cycled. Nothing was wasted. The fact that this cycling required sharing your house with cows was just part of how the system worked. You couldn't opt out of one part without affecting everything else. The modern romanticization of medieval life rarely includes accurate depictions of these living arrangements. When movies or television shows portray medieval peasant life, they usually show separate houses and barns because showing the historical reality would seem too alien to modern audiences. We can accept swords and castles and even open hearth cooking, but cows in the kitchen? That's apparently a bridge too far for contemporary sensibilities. Which is a shame, really, because it means we're not understanding the actual material reality of how most people lived for most of history. So here's the fundamental point about living with livestock that I want you to take away. It wasn't degrading or shameful or a sign of failure. It was practical engineering that solved multiple problems using available resources. Medieval people weren't suffering through this arrangement. They were benefiting from it. Yes, there were downsides. Yes, it involved smells and mess and management challenges. But the benefits, warmth, security, convenience, improved animal health, integrated waste management, outweighed those downsides given the alternatives available at the time. And if you're sitting there in your modern, centrally heated, animal-free home feeling superior about how far we've come, consider this. Your heating system probably relies on natural gas or electricity generated from fossil fuels, both of which are non-renewable resources with significant environmental costs. Your food comes from agricultural systems that separate animals from their waste, requiring synthetic fertilizers to maintain soil fertility. You're probably completely disconnected from the realities of where your food comes from and what it takes to produce it. The medieval peasants sharing their house with a cow understood their entire material economy in ways most modern people don't. They might not have had our comfort or convenience, but they had integration and comprehension we've lost. That's worth thinking about, even if you're not planning to move a cow into your living room anytime soon. So we've covered the major structural elements: frames, walls, roofs, even the livestock heating system that modern people find so baffling. But here's the thing about medieval buildings: they weren't airtight. Between those wattle and daub panels around window shutters, through gaps in door frames wherever two materials met, you had potential air infiltration. And air infiltration in winter meant heat loss, which meant cold misery, which meant increased risk of freezing to death. Medieval builders couldn't just run down to Home Depot for spray foam insulation or weather stripping, but they absolutely understood the problem and developed solutions using materials they could gather from their immediate environment. Welcome to the world of natural insulation, where the answer to heat loss was literally growing in the woods and fields around your house. The concept of stuffing gaps with soft, fibrous material to block drafts isn't rocket science. It's intuitive. Anyone who's felt wind whistling through a crack understands that filling that crack would help. What's impressive is how medieval people systematically identified the best materials for this purpose and developed harvesting, processing, and application techniques that made natural insulation genuinely effective. This wasn't random trial and error. This was accumulated knowledge refined over generations, passed down as practical wisdom that every household needed to know. Let's start with moss, which was probably the single most important gap-filling material in medieval England, and continues to be used in traditional building restoration today. When we say moss, We're primarily talking about sphagnum moss and various other moss species that grow abundantly in damp environments throughout England, which, given that this is England, means pretty much everywhere. Moss has several properties that make it ideal for insulation. It's soft and compressible, so you can stuff it into irregular gaps. It's fibrous, so it stays in place once installed rather than immediately falling out. And crucially, it's naturally antimicrobial and rot-resistant, meaning it won't decay quickly even when exposed to moisture. The antimicrobial properties of sphagnum moss are actually quite remarkable and were unknowingly exploited by medieval builders. Sphagnum contains compounds that inhibit bacterial and fungal growth, which is why you can harvest moss that's been sitting in a bog for who knows how long, and it's still fresh and viable rather than rotted into mush. This same property means that moss stuffed into your walls will resist decay even in the damp English climate. Modern research has confirmed that sphagnum moss has genuine antiseptic qualities. It was used as wound dressing in both world wars for exactly this reason. But medieval people just knew that moss lasted longer than other organic materials in similar applications. Harvesting moss was straightforward but time-consuming. You'd go to areas where moss grew thickly, bogs, wet woodlands, shaded areas near streams, and simply pull up handfuls of it. Moss doesn't have deep roots, so it comes up easily. The trick was getting enough quantity to make the trip worthwhile while not completely stripping an area, which would prevent regrowth. Medieval people understood sustainable harvesting even if they didn't use that terminology. You took what you needed but left enough that the moss colony could recover. The processing of moss for insulation was minimal, basically just letting it dry somewhat if it was too wet to work with comfortably. You didn't want it bone dry because completely dried moss becomes brittle and crumbly. You wanted it with some retained moisture but not dripping wet. The ideal consistency was similar to a wrung-out sponge, damp enough to be flexible and compressible, but not so wet that it would create moisture problems in your walls. Medieval builders developed an intuitive sense for proper moss moisture content through experience. The application technique for moss insulation was simple. Identify gaps, stuff moss into them until they're filled, pack it down reasonably firmly but not so tight that you can press it into a solid mass. The insulation value comes from the trapped air spaces within the moss structure, so overcompression defeats the purpose. You wanted the moss to fill the gap and stay in place while maintaining its lofty structure. This was usually accomplished by hand. You'd tear off chunks of moss appropriate to the size of the gap you were filling and work it in with your fingers, adding more until the gap was completely filled. The locations where moss insulation was most critical included the gaps between wattle and door panels and the timber frame, around window openings where shutters met the frame, around door jambs, at the junction between walls and roof, and anywhere else where two different building elements met and created potential air leakage paths. Medieval builders became skilled at identifying these thermal weak points, running their hands along walls on windy days to feel where air was infiltrating, then targeting those specific areas for moss treatment. The maintenance schedule for moss insulation was ongoing and seasonal. Before winter, you'd do a comprehensive check of your building, refreshing moss in areas where it had compressed, fallen out, or been removed by birds looking for nesting material. Birds were actually a significant problem. They loved the soft, dry moss for their nests and would pull it out of gaps if they could access it. Some buildings show evidence of protective measures like small wooden or wattle panels installed over moss-packed gaps to prevent bird theft, which is both adorable and practical. Now let's talk about wool, which served multiple insulation functions in medieval buildings and shows up in ways that modern people often don't think about. Wool is an incredible material. It's insulating even when wet. It's naturally fire-resistant, it's durable, and in medieval England it was abundant. England's economy was substantially based on wool production for most of the medieval period. Every household with access to sheep had wool, and those without could usually obtain it through trade or as byproduct from textile production. The wool used for insulation wasn't the nice, clean, processed wool that went into making cloth. This was waste wool. The rough, dirty, short fibres that couldn't be spun effectively. The wool pulled from dead sheep, the bits left over from shearing that were too matted or contaminated to be worth processing for textiles. This waste wool, which had minimal economic value for other purposes, was perfect for insulation. It was essentially free if you had sheep, and even if you had to trade for it, it was cheap because nobody else wanted it for anything better. The insulation applications for wool included stuffing it into gaps alongside or instead of moss. Wool was particularly good for larger gaps where its cohesiveness helped it stay in place. It was sometimes mixed with moss to create a combined insulation that took advantage of both materials' properties. Wool was packed between layers in walls where access was possible, creating cavity insulation that's conceptually identical to modern blown-in insulation, just accomplished with raw sheep wool instead of fiberglass or cellulose. One particularly clever use of wool was in door and window coverings. Heavy wool fabric, usually rough, undyed material that wasn't suitable for clothing, would be hung over door openings in winter, creating an insulating curtain that blocked drafts while still allowing passage. The fabric could be pushed aside when you needed to go through, then fell back into place behind you. This is basically the medieval version of those plastic strip curtains you see in warehouses to separate climate-controlled areas from uncontrolled spaces. Same principle, different materials, but equally effective. The processing of wool for insulation purposes was minimal since you were using waste wool that by definition didn't require the careful cleaning and carding that textile quality wool needed. You might shake out the worst of the dirt and debris, but that was about it. Lanolin, the natural oil in sheep's wool, was actually beneficial for insulation purposes because it provided water resistance and helped the wool maintain its loft over time. Clean, lanolin-free wool would have been less effective, though medieval people probably didn't understand the chemistry behind why greasy wool worked better. The fire resistance of wool is worth emphasizing because thatch roofs meant fire was a constant concern. Wool has a naturally high ignition temperature and tends to self-extinguish when the flame source is removed. It doesn't burn well, which made it safer than many alternatives for insulation near hearths and chimneys. Medieval builders probably noticed empirically that wool near fires didn't ignite as readily as straw or other materials, and incorporated this observation into their building practices. Any material that reduced fire risk was valuable. Now we need to discuss floor coverings, which served insulation functions that went beyond just comfort. The typical medieval floor was earth, packed dirt or clay that formed a reasonably solid surface but was cold, hard, and damp. Walking or sleeping directly on such floors was unpleasant and contributed to heat loss from the building. The solution was to cover the floor with thick layers of organic material that provided insulation from the ground, cushioning for walking and sitting, and some degree of moisture management. Rushes were the most common floor covering throughout medieval England. Rushes are marsh plants that grow in dense stands in wet areas, and they're perfect for floor covering purposes. They're long, straight, and relatively uniform. When dried, they're tough and springy, creating a resilient mat underfoot. They're hollow inside, which gives them insulation value through trapped air. And crucially, they were abundant and free for the gathering, making them accessible to even the poorest households. The harvest season for rushes was typically late summer when the plants were fully grown, but before they started dying back for winter. Medieval families would go to marshes and cut rushes in large bundles, then transport them home to dry. The drying process was important. Wet rushes would rot and create a slimy, smelly mess on your floor. Properly dried rushes would last months before needing replacement. The quantity needed was substantial. A typical medieval cottage might require several dozen large bundles of rushes to create adequate floor coverage, and you'd need to replace this covering at least once or twice per year, as it broke down from foot traffic and use. The application method for rush flooring was delightfully simple. You literally just threw handfuls of rushes on the floor and spread them around until you had reasonably even coverage 6 to 12 inches deep. That's it. No elaborate installation procedure, no special techniques. Just scatter the rushes and walk on them. The foot traffic and daily activities would naturally pack them down somewhat and distribute them evenly over time. When fresh rushes were added, which happened regularly as the top layer wore out, they'd be scattered on top of the existing layer, creating a multi-layered floor covering that composted slowly from the bottom while remaining fresh on top. This practice has gotten a bad reputation in popular history because there's a famous quote from Erasmus, a 16th century scholar visiting England, describing floors as disgusting accumulations of filth where rushes were never completely removed but just had new layers added on top, creating what he delicately described as containing spittle, vomit, the urine of dogs and men, beer, scraps of fish, and other filth. Which, okay, that sounds absolutely revolting, and Erasmus was not wrong that some households let their floor rushes get disgusting. But Erasmus was also a bit of a snob, writing about what he perceived as primitive English practices, and he was probably describing worst-case scenarios rather than typical conditions. In normally maintained households, floor rushes were completely replaced regularly, typically every few months. You'd gather up all the old rushes, haul them out to the midden or compost heap and put down fresh ones. This refresh was often timed to seasons, a thorough clean-out in spring, another in fall, with regular additions of fresh rushes on top during the intervening months. The old rushes, thoroughly composted and mixed with household waste, made excellent fertilizer. So the cycle continued. Rushes from the marsh became floor covering, absorbed household debris and waste, then returned to the land as soil amendment. Everything circled back. The aromatic herbs mixed into floor rushes deserve special attention, because this practice shows medieval people's understanding of aromatic properties and air quality management, even if they didn't understand the underlying chemistry. Common herbs added to floor rushes included lavender, which smelled pleasant and had insect-repelling properties; mint, which provided fresh scent and also deterred pests; chamomile, which released pleasant fragrance when stepped on; meadowsweet, which was particularly popular because it produced a sweet, honey-like scent when crushed; tansy, which was believed to repel fleas and other insects, though whether it actually worked is debatable. These aromatic additions weren't just about making the house smell nice, though that was certainly a factor. Many of these herbs have genuine insect-repelling properties due to the volatile compounds they contain. Modern research has confirmed that lavender, mint, and several other traditional strewing herbs do deter various insects through their scent. Medieval people didn't know about volatile organic compounds or insect pheromone disruption, but they knew empirically that houses with lavender in the floor, rushes seemed to have fewer flea infestations than houses without. That was evidence enough. The gathering of strewing herbs was typically a summer activity when herbs were flowering and most fragrant. Families would collect herbs from gardens, fields, and hedgerows, then dry them for winter use. The dried herbs would be mixed into fresh floor rushes when they were laid down, creating a fragrant carpet that would release scent as it was walked upon. Wealthier, poorer households might use whatever aromatic plants they could gather for free, which might be a less impressive selection, but still better than nothing. The social status signalling through floor coverings was real and noticeable. A house with thick, fresh rushes mixed with expensive herbs like lavender was clearly a wealthier household. A house with thin, old rushes and no herbs was marking itself as poor. Special occasions might warrant putting down extra fresh rushes and generous herbs, when important guests were expected, for instance, or for holiday celebrations. This practice shows up in literature and records of the period, with references to strewing the hall with fresh rushes as preparation for important events. Now let's talk about wall hangings, which served crucial insulation functions while also providing aesthetic value. Medieval buildings, as we've established, had walls that were somewhat porous to air movement. Wattle and daub did a good job of blocking wind, but it wasn't perfect, and the junction between walls and other structural elements created potential air leakage paths. Hanging fabric on walls created an additional barrier, an insulating layer of still air trapped between the fabric and the wall that significantly reduced heat loss. The fabrics used for wall hangings varied by social status and available resources. Wealthy households had tapestries, elaborate woven artworks that cost fortunes and showed off the owner's wealth, while also providing excellent insulation. The middle ranks might have painted cloths, cheaper alternatives to tapestries that provided similar insulation value, if not the same artistic prestige. Poor households might hang any available fabric, rough wool cloth, old blankets, even animal skins if they had access to them. The key was creating that insulating air layer, and almost any flexible material would work for that purpose. The installation of wall hangings was usually quite simple. Fabric was hung from hooks or pegs driven into the wall or attached to the timber frame. The hangings didn't need to be stretched tight or fastened at the bottom. In fact, leaving them loose was actually better for insulation, because it allowed the fabric to drape and create more airspace behind it. Some households would layer multiple fabrics, a rough outer layer with something finer inside, creating enhanced insulation through multiple air gaps. The practical benefits beyond insulation included reducing drafts. Even if air was leaking through your walls, it had to get through the hanging fabric first, which slowed it down and spread it out so you didn't get concentrated cold drafts hitting you. Wall hangings also absorbed sound, making interiors quieter and more pleasant. They helped manage moisture by absorbing excess humidity from cooking and breathing, then releasing it more slowly, which reduced condensation problems. And obviously, they made spaces more attractive, particularly important for wealthier households who used their halls for entertaining and needed to project appropriate status. The seasonal adjustment of wall hangings was common practice. Heavy wool hangings would go up in fall and stay through winter, providing maximum insulation during cold months. In summer, lighter fabrics might replace them, or they might be removed entirely to allow better air circulation. This seasonal rotation was labour-intensive, Taking down, storing, and later rehinging substantial fabric panels wasn't quick work, but the comfort improvement was worth the effort. The maintenance of wall hangings included periodic taking down and airing, or beating to remove dust and accumulated debris. Heavy wool hangings in a smoky medieval house would accumulate soot and odours, and while medieval people's tolerance for these things was higher than ours, there were limits. A thorough spring cleaning often involved removing wall hangings, beating them outside to remove dust, airing them for days, sometimes washing them if they were too grimy, then rehanging them. This labour-intensive process was one reason why poorer households might have minimal wall coverings. The maintenance burden was real. The combination of all these insulation strategies, moss in gaps, wool in cavities, rushes on floors, fabric on walls, created a layered defence against heat loss that was genuinely effective. No single element was dramatically effective in isolation, but together they added up to significant improvements in thermal comfort. A medieval building with all these measures in place would be noticeably warmer than one without them, possibly the difference between needing a fire constantly versus only needing it in the evenings and overnight. The cumulative insulation value is difficult to quantify precisely because there are so many variables. How thoroughly were gaps filled? How thick was the floor rush layer? What quality and quantity of wall hangings were used? But modern experimental archaeology suggests that these traditional insulation methods could reduce heat loss by perhaps 30 to 40% compared to an uninsulated structure. That's substantial. That's the difference between burning through your firewood supply in January versus making it last until March. The knowledge systems around these insulation practices were transmitted informally but systematically. Young people growing up in medieval households would learn from parents and grandparents which mosses worked best for chinking, where to find good rushes, when to harvest them, how thickly to lay them, which herbs to mix in. This wasn't formal education, nobody sat down for lectures on insulation theory, but it was comprehensive practical training that happened through daily participation in household management. The gendered division of labour around insulation materials is worth noting. Gathering moss and rushes could be done by anyone, though it was often work assigned to children or teenagers. Processing wool was typically women's work, part of the broader textile production that was a primary female responsibility in medieval households. Hanging wool fabrics might be done by either gender depending on the household. The point is that managing natural insulation was a household responsibility that drew on labour from all members, not specialised work done by expert tradespeople. The economic value of these natural insulation materials being essentially free or very cheap had enormous implications for housing quality across economic classes. A poor family couldn't afford glass windows or tile roofs, but they could gather moss and rushes. They could obtain waste wool. They could hang rough cloth on their walls. These accessible insulation methods meant that even modest households could achieve reasonable thermal comfort. The gap in comfort between rich and poor households was real, but not as dramatic as it would be if insulation required expensive materials. The environmental sustainability of these practices is striking from a modern perspective. Everything was renewable, locally sourced, and biodegradable. There were no supply chains, no industrial processing, no resource depletion, no persistent pollution. The moss grew back. The rushes regrew annually. Sheep produced new wool every year. Old insulation materials composted and enriched soil. The whole system was circular and sustainable in ways that modern building practices rarely achieve. The connection to the landscape that these practices required is worth emphasizing. Medieval people needed to know their local environment intimately to effectively insulate their homes. They needed to know where moss grew, where the best rush beds were, when and how to harvest without depleting resources. This wasn't abstract or theoretical knowledge. It was practical understanding of local ecology that directly impacted survival and comfort. Modern people generally lack this depth of connection to local landscapes, having outsourced our material needs to industrial supply chains. The loss of these traditional practices represents a loss of knowledge that's difficult to recover. Some of it has been preserved through continuous practice by people maintaining historic buildings or through experimental archaeology, but much of the nuanced, experiential knowledge has vanished. Modern people attempting to use traditional insulation materials often have to rediscover through trial and error what medieval people knew instinctively from lifelong experience. How tightly to pack moss for optimal insulation without overcompression. How free. These questions have answers based in experience that can't be completely captured in written instructions. The rediscovery of natural building materials by modern sustainable building advocates shows that medieval practices were actually quite sophisticated. Contemporary builders experimenting with sheep's wool insulation, cork, hemp fibre and other natural materials are essentially reinventing approaches that were standard practice centuries ago. The difference is that modern builders can measure thermal resistance values and optimize scientifically, while medieval builders relied on empirical observation and accumulated wisdom. But the end result, effective insulation using renewable local materials, is remarkably similar. The modern building industry's reliance on synthetic materials, fiberglass, foam insulation, vinyl, plastics, represents a dramatic break from thousands of years of building with natural materials. These synthetic materials have advantages in some respects: higher insulation values per inch thickness, more consistent properties, longer lifespan in some applications. But they also have disadvantages that are becoming increasingly apparent. They're often toxic in production or installation. They don't biodegrade. They require industrial manufacturing. They're typically not locally sourced. The medieval approach, using materials that could be gathered from surrounding landscape, is looking more sensible as environmental concerns become pressing. The practical wisdom encoded in medieval insulation practices is that you work with what you have, you use materials that suit your climate and building type, and you accept that maintenance is ongoing rather than expecting materials to last forever without attention. These principles are actually quite sophisticated and represent mature understanding of buildings as living systems rather than static objects. Modern building culture, with its expectation of maintenance-free materials and permanent installations, is arguably less realistic about how buildings actually function over time. So here's what I want you to take away from all this talk about moss and wool and rushes and wall hangings. These weren't desperate measures by people who didn't know better. These were thoughtful, effective solutions to genuine problems, using materials that were appropriate to the circumstances. Medieval, they couldn't run to the store for a roll of fiberglass insulation, but they could gather moss from the bog, wool from their sheep, rushes from the marsh. And with those simple materials, applied with knowledge accumulated over generations, they created homes that were genuinely comfortable even in harsh English winters. The fact that we've largely abandoned these practices in favour of industrial materials doesn't mean the old ways were inferior. It means we've chosen different trade-offs. We've prioritised convenience and performance over local sourcing and sustainability. We've accepted toxic materials and industrial supply chains in exchange for better insulation values and less maintenance. These are legitimate choices, but they're choices, not inevitable progress. Medieval people made different choices based on different priorities and constraints, and their solutions worked remarkably well for their context. That deserves recognition, not condescension. We've spent a lot of time talking about individual buildings, how to construct them, insulate them, heat them with livestock and natural materials. But here's something that doesn't get enough attention when we think about medieval survival. Buildings didn't exist in isolation. They were part of communities, and those communities made deliberate choices about how to arrange themselves in space. And those spatial choices had enormous implications for thermal comfort and survival. Welcome to the world of social architecture, where the placement of your neighbour's house relative to yours might matter as much as your own roof for making it through winter alive. Modern people are used to thinking about housing as individual units optimised for privacy and personal space. We want yards between houses, ideally substantial ones. We value distance from neighbours as a marker of success. The wealthy live on large plots with significant separation from others. The idea of deliberately building houses close together, sharing walls, clustering dwellings around communal spaces, these read as compromises forced by poverty or urban density, not as positive choices. But medieval village planning operated on completely different principles, and those principles were shaped heavily by the physics of heat retention and wind protection. Let's start with the most basic concept: windbreaks. Wind is a massive factor in thermal comfort, something we've touched on before but needs emphasis here. Wind dramatically increases heat loss from buildings through two mechanisms. First, it creates air infiltration. It forces cold outside air through any gaps in your structure, while simultaneously pulling warm inside air out. Second, it increases convective heat loss from exterior surfaces. Wind moving across your walls carries away heat much more efficiently than still air. The difference between a calm day at 35 degrees and a windy day at the same temperature is enormous in terms of how cold it feels and how much fuel you need to burn to stay warm. Medieval builders understood this empirically. They knew that buildings exposed to prevailing winds were harder to heat and required more firewood. They knew that structures sheltered by other buildings or landscape features were more comfortable. And they made deliberate choices about village layout to minimize wind exposure. choices that show up consistently in medieval settlement patterns across England. These weren't random decisions or the result of gradual unplanned accretion. Medieval villages had structure, and that structure served thermal and practical purposes. The typical medieval English village wasn't a grid of evenly spaced houses like a modern subdivision. It was clustered, usually arranged around some central feature: a village green, a church, a manor house, a crossroads. Houses were built close together, often sharing walls or with minimal space between them. This clustering wasn't about maximising land use in the modern sense. There was plenty of agricultural land available around the village. It was about creating mutual protection from wind and weather, while also facilitating social interaction and communal defence. The orientation of buildings within the cluster mattered significantly. In most of England, prevailing winds come from the southwest and west. Medieval builders positioned houses and outbuildings to create windbreaks for each other, with structures arranged so that wind hitting the village would be blocked or deflected by buildings before it could sweep through the entire settlement. The most exposed positions, typically the western edge of the village, might have sturdier buildings, barns, or even deliberately positioned hedges and walls to provide wind protection for the houses behind them. Archaeological and historical evidence shows this deliberate planning in action. Village layouts weren't haphazard. There was logic to which buildings went where, and part of that logic was thermal. The church, being a substantial stone structure, might anchor one end of the village, providing wind protection and serving as a landmark. The manor house would be positioned with attention to both status considerations and practical shelter. Common houses would cluster around these anchor points, creating dense nodes of habitation that provided mutual protection. The advantages of this clustering for thermal comfort are significant and measurable. A house surrounded by other houses on multiple sides has less exposed surface area to the elements. If you've got buildings to your north and west, the directions cold winds typically come from in England, your own structure is partially sheltered. Your heat loss through walls goes down. Your fuel requirements decrease. Your comfort improves. It's cooperative thermal engineering through spatial arrangement. The shared wall concept takes this clustering to its logical conclusion. When two houses share a wall, that entire wall surface is no longer exposed to exterior conditions. It's now modern attached housing and row houses use exactly this principle, though we've forgotten that it was originally a thermal strategy rather than just a way to fit more housing into limited space. Medieval buildings with shared walls show up frequently in both archaeological remains and surviving structures. Sometimes these were purpose-built as connected units, essentially medieval row houses. Sometimes they developed over time as new buildings were constructed directly against existing ones, either deliberately or because available space was limited. The archaeological signature is clear. You can see where two buildings shared a common wall, with that wall often being more substantial than the external walls because it had to serve both structures and bear loads from two roofs. The construction implications of shared walls required coordination between neighbours. You couldn't just slap your wall against someone else's building without discussion. You needed agreement about where exactly the shared wall would go, how high it would be, how loads would be distributed, what materials would be used. This coordination meant that building houses wasn't purely an individual endeavour. It was a communal process that required negotiation and cooperation, which reinforced social bonds while also improving everyone's housing situation. The legal and social frameworks around shared walls in medieval England were complex and show up in manor court records and village bylaws. Disputes over shared walls were common. One party wanted to modify or rebuild, the other objected, or disagreements arose about who was responsible for maintenance. These disputes tell us that shared walls were both valued and contentious, which makes sense. The thermal and structural benefits were real, but so were the complications of having your housing literally connected to your neighbours. You couldn't burn down your own house without threatening theirs, which occasionally mattered. Now let's talk about the village green or common area, which served multiple functions, including thermal and social ones that aren't immediately obvious. Most medieval villages had some kind of central open space, sometimes a formal green, sometimes just a widened area where roads met, sometimes the space around the church. These spaces served practical purposes like providing areas for communal activities, markets and gatherings, but they also functioned as heat sinks and weather buffers in ways that shaped village life. During the day, open spaces absorbed solar heat, particularly in summer but even on sunny winter days. This heat was stored in the ground and radiated back overnight, creating slightly milder microclimates in the immediate vicinity. The effect wasn't dramatic. We're talking maybe a degree or two of temperature difference. But when you're operating on margins where a few degrees determines comfort versus misery, these small effects matter. Villages with well-designed central spaces had marginally warmer overnight temperatures than more dispersed settlements, and medieval people probably noticed this empirically, even if they couldn't explain the thermodynamics. The communal fire on the village green is something that shows up in medieval records and literature, but is often dismissed as a romantic notion rather than practical reality. But communal fires were absolutely a real feature of medieval village life, particularly during winter and on special occasions. These weren't cooking fires. Those stayed in individual houses. These were gathering points, social spaces that happened to also provide warmth to anyone who stood near them. On cold, the practical benefits of communal fires went beyond just providing warmth to people standing around them. A large fire burning in a central location created a warm updraft that affected air circulation patterns in the surrounding area. It also served as a clear landmark and meeting point. If you needed to find someone or conduct business, you went to the fire. It was the medieval equivalent of meet me at the Starbucks, except instead of overpriced coffee, you got actual warmth and the smell of wood smoke in your clothes, which probably seemed like a reasonable trade-off. The fuel for communal fires was often contributed collectively, with households bringing wood to maintain the fire in rotation. This shared responsibility meant that no single family bore the full cost of providing a communal resource, while everyone benefited from having a central gathering point with warmth and light. The system worked because it was in everyone's interest to maintain it. You contributed wood because you knew you'd benefit from the fire's warmth and the social opportunities it provided. This kind of mutual aid system is typical of medieval communal organisation. The timing and duration of communal fires varied by season, weather, and local tradition. In deep winter, a village might maintain a fire continuously for weeks, with someone always responsible for keeping it going. In milder weather, fires might only be lit in the evenings when people were free to gather. Special occasions, festivals, market days, communal work projects would certainly feature fires regardless of weather. The fire served as a focal point for community life in ways that made it much more than just a heat source. The social architecture of medieval villages extended beyond just building placement and communal fires. The network of paths, lanes, and spaces between buildings was deliberately organized to facilitate movement while providing shelter. Lanes weren't necessarily straight or optimally efficient from a modern urban planning perspective. They curved, narrowed, widened, all in ways that created protected passages between buildings. Walking through a medieval village, you'd rarely be in completely open, wind-exposed space. The buildings, walls, hedges, and other features created a network of partially sheltered routes. This protective network meant that winter movement through the village was less miserable than it might otherwise be. You weren't walking across open fields getting blasted by wind the whole way. Medieval people would have known the most sheltered routes by heart and used them preferentially in harsh weather. This kind of practical knowledge, which path to take when the wind is from the west, where to walk when it's raining, was part of everyday life wisdom that everyone accumulated through experience. The relationship between house placement and agricultural fields is worth considering because it affected daily life significantly. Medieval villages typically had houses clustered together with agricultural fields surrounding them. This meant this separation of residence and workplace allowed for the thermal advantages of clustering while still providing agricultural productivity. A village with houses close together was easier to defend than scattered farmsteads. You could more easily maintain watch, raise alarm, and provide mutual aid if threatened. While major military threats weren't a daily concern for most medieval English villages, the possibility of raids, bandits, or local conflicts was real enough that defensive considerations influenced settlement patterns. The fact that defensive clustering also provided thermal benefits made it doubly attractive. The gradual evolution of village layouts over time shows increasing sophistication in spatial organisation. Early medieval settlements often show less organised clustering, houses somewhat randomly positioned within a general area. Later medieval villages show more deliberate planning, streets with clear organisation, building plots of relatively standard sizes, evident thought about orientation and relationships between structures. The regional variations in village layout across England reflect different environmental conditions, agricultural systems, and cultural traditions. Villages in exposed upland areas tended toward tighter clustering for wind protection. Lowland villages with more temperate conditions might spread out more. Areas with nucleated villages, tight clusters of houses, contrasted with regions featuring more dispersed settlement patterns. These variations weren't random. They represented adaptations to local conditions and needs. The relationship between social status and position within the village cluster is revealing. The most desirable positions, sheltered from prevailing winds, close to central amenities, with good access to key resources, tended to be occupied by higher status households. The manor house would typically be in a favoured position. The church occupied prominent central space. Wealthier peasants would have houses in more protected positions. Poorer households might find themselves in more exposed positions at the village margins. This spatial hierarchy reinforced social hierarchy, with status literally mapped onto the landscape. The economic implications of clustered living included shared infrastructure and resources. A village with houses close together could more easily maintain communal resources like wells, ovens, and mills. The paths between houses needed less maintenance than if everyone lived spread out. Communication and coordination were easier. Trade and exchange were facilitated. These economic efficiencies weren't trivial. They meant that villages operating as communities could achieve things that isolated households couldn't, and everyone benefited from these collective capabilities. Someone had to clean the village green, maintain communal paths, manage the communal fire, keep the well in good repair. Medieval villages handled this through various systems, required labour contributions, rotating responsibilities, appointments of specific individuals to handle certain tasks. The point is that maintaining the physical infrastructure that provided thermal and practical benefits was a community responsibility that required active, ongoing effort. The tension between individual interests and communal needs played out constantly in village life. You might want to expand your house in a direction that would block a communal path. Your animals might damage the village green. Your construction might affect your neighbour's wall or drainage. These conflicts required resolution through negotiation, manor court decisions, or village bylaws. The documentation of these disputes in medieval records tells us that balancing individual and collective interests was an ongoing challenge, not a solved problem. The seasonal rhythms of village life were partly structured by the thermal challenges of winter. During summer, with longer days and pleasant weather, social life could spread out into fields and surrounding areas. People worked dispersed across the landscape and gathered where convenient. Winter concentrated social life back into the village core. The communal fire became more important. The sheltered lanes saw more use. Houses became social spaces in ways they might not be in summer, when outdoor gathering was more pleasant. The physical structure of the village enabled this seasonal flexibility. The role of children in medieval village social architecture is worth considering. Children growing up in clustered villages had playmates close by, which affected childhood experience and social development. They learned the geography of village space intimately, which lanes led where, which buildings blocked wind from which directions, where the good spots were for various activities. This childhood knowledge of village space became practical adult knowledge about where to go in different weather conditions, where to meet people, how to move efficiently through the settlement. The church served obvious religious functions, but also functioned as the most substantial structure in most villages, providing both physical wind protection and social centrality. The churchyard, the cemetery surrounding the church, was both sacred space and communal gathering area. Village meetings might be held there. It served as a focal point for processions and festivals. The thermal benefits of having a large stone structure at the heart of your village were secondary to its religious importance, but were nonetheless real. As villages grew, new houses would be added in patterns that maintained or improved wind protection and communal structure. As they shrank, which happened due to plague, economic changes, or other factors, the remaining buildings would still maintain some degree of clustering. Villages could reorganize over time in response to new needs or opportunities, while maintaining the basic principles of clustered, mutually protective settlement. The documentation of village layouts in medieval sources is frustratingly limited because, once again, it was too obvious to write about in detail. You see oblique references, mentions of the green, descriptions of property boundaries that reference neighbouring buildings, records of disputes about shared walls or blocked paths. Later maps and surveys provide more detailed information, but often miss the subtle spatial relationships that mattered for daily life. Reconstructing medieval village layouts requires combining limited documentary evidence with archaeological finds and analysis of surviving village structures where they exist. The comparison to modern suburban sprawl is instructive. The result is thermally inefficient. Every house is exposed on all sides, wind protection is minimal, distances between houses preclude shared walls or mutual sheltering. We heat and cool these isolated structures at enormous energy cost, basically fighting against the inefficient spatial organization we've chosen. Medieval clustered villages, by contrast, worked with thermal realities rather than against them. The contemporary movement toward new urbanism and traditional neighborhood development is essentially rediscovering principles that medieval villages embodied: walkability, mixed use, buildings close together, streets designed for people rather than just cars, communal spaces that foster social interaction. These aren't novel ideas. They're ancient principles that worked for centuries and were abandoned relatively recently in favor of automobile-oriented development. The fact that planners are now trying to recreate aspects of traditional settlement patterns suggests that maybe medieval people knew what they were doing with their village layouts. The loss of traditional village structure in England through enclosure movements, industrialization, and modern development has been accompanied by loss of the thermal and social benefits that clustering provided. Modern rural settlements often feature scattered housing, individual houses on substantial plots spread across the landscape. These isolated houses require more energy to heat, provide less wind protection, and don't facilitate the kind of casual social interaction that clustered villages enabled. We've gained privacy and space, but lost communal efficiency and resilience. The archaeological study of medieval village layouts has become increasingly sophisticated, using techniques like geophysical survey, aerial photography analysis, and GIS mapping to reconstruct settlement patterns. These studies reveal the logic and organization of medieval settlements in ways that weren't visible before. We can now map entire village layouts, trace the evolution of street patterns, identify building clusters and their relationships, understand how communities organize space over time. This research confirms that medieval villages weren't haphazard, but carefully structured to serve multiple needs simultaneously. The experimental archaeology of communal living, attempts by modern people to recreate medieval village life, consistently confirms the value of clustering and communal resources. Groups that have tried living in reconstructed medieval villages report that having neighbors close by, sharing resources and working collectively provides both practical advantages and social benefits. The thermal advantages of clustered housing are measurable in reduced fuel consumption and improved comfort. They were collective accomplishments that required community organization and cooperation. Your ability to make it through winter depended partly on your own building and preparation, but also on how your house related to your neighbors' houses, whether the village was well organized for wind protection, if communal resources like fires and sheltered paths were maintained. The modern individualist ethos, everyone responsible for their own comfort and security, minimal dependence on neighbors or community, would have struck medieval people as both impractical and undesirable. Impractical because the thermal and defensive benefits of clustering were too valuable to sacrifice for marginal gains in privacy. Undesirable because social interaction, communal labor, and shared resources were valued parts of life, not unfortunate necessities to be minimized. The physical organization of villages both reflected and reinforced these communal values. So when you're thinking about medieval winter survival, don't just think about individual buildings and families huddled inside them. Think about villages as integrated systems where multiple buildings, communal spaces, shared resources, and social organization all work together to make life bearable and sometimes even comfortable. The shared walls weren't poverty measures, they were thermal engineering. The communal fire wasn't just a nice tradition, it was practical infrastructure that served multiple needs simultaneously. Medieval villages were designed systems, not random assemblages, and those designs reflected sophisticated understanding of how to create livable environments given available resources and technology. And if you think about it, there's something appealing about the medieval model, a community organized for mutual benefit, where everyone contributes to collective resources and everyone gains from collective efficiencies. We've traded that for individual autonomy and privacy, which has benefits, but it's worth remembering what we've given up in the exchange. The warmth of a communal fire on a cold night wasn't just physical heat. It was the warmth of community, of shared experience, of knowing you weren't facing winter alone. That's worth something, even if it's hard to quantify in BTUs or degrees Fahrenheit. But here's something we need to address. Not everyone was living in wattle and daub cottages with cows in the next room. Medieval England was a deeply stratified society where your social class determined pretty much everything about your life, including how and where you lived. And this is where we encounter one of the most delicious ironies in medieval history. The people at the top of the social hierarchy, living in impressive stone castles and manor houses, were often significantly less comfortable in winter than the peasants they ruled over. Welcome to the paradox of medieval thermal comfort, where having more money and status could actually make you colder. Let's start with your typical 13th century English peasant family. Let's say a husband, wife, 3 kids, maybe a surviving grandparent, would be living in a structure that was maybe 30 to 40 feet long and 15 to 20 feet wide. Not huge by modern standards, but adequate for its purpose. The thermal characteristics of this peasant cottage were actually pretty good for a structure built with minimal resources. You had thick walls providing decent insulation and thermal mass. You had a substantial thatched roof creating excellent insulation overhead. You had livestock contributing heat. You had small windows, if any, minimizing heat loss through openings. You had a compact interior space that was relatively easy to heat with a modest fire. The whole structure was optimized, whether deliberately or through generations of trial and error, for thermal efficiency. It wasn't luxurious, but it worked. The heating system in a peasant cottage centered on a single hearth, usually located relatively centrally in the living space. This would be an open fire, just a designated area of the floor where you built fires for cooking and heating. Smoke would rise up and eventually find its way out through gaps in the thatch or a designated smoke hole, though eventually is doing a lot of work in that sentence because medieval cottages were definitely smoky. The fire was fed with whatever wood could be gathered locally, supplemented sometimes with peat or dried dung if wood was scarce. Fuel efficiency mattered because gathering fuel was labour-intensive, so you didn't waste it. The social organisation of the peasant cottage meant that everyone basically lived in one room. Privacy as we understand it didn't really exist. The family slept together, probably on straw mattresses on the floor or on simple wooden platforms, often sharing bed spaces for warmth. Cooking, eating, working, sleeping, entertaining visitors, it all happened in the same space. This sounds horrifically cramped to modern sensibilities, but it had the advantage that one fire could heat the entire living space because the entire living space was one room. Thermal efficiency through simplicity. Now let's move up the social ladder to yeoman farmers or more prosperous peasants. People who had a bit more wealth and resources. Their houses might be somewhat larger, perhaps with a separate solar, a small private chamber off the main hall for sleeping. The construction materials might be slightly better quality, more carefully selected timber, better finished walls, perhaps some glass in the windows if they were really doing well. But fundamentally, the thermal strategies remained similar to poorer cottages. You still had relatively compact spaces, thick walls, substantial roofs, and heating centered on open hearths. The prosperity showed in larger size and finer finishes, not in dramatically different thermal technology. The merchant class in towns presents an interesting middle ground. Urban space, the shared walls provided excellent thermal benefits we've already discussed. The urban location meant better access to purchased goods, so you might have glass windows, better quality fabrics for wall hangings, imported woods for furniture and panelling. But urban merchant houses often featured improvements like glazed windows, which was a genuine luxury. Glass let in light while keeping out wind, dramatically improving comfort compared to shuttered openings. A house with multiple glazed windows was signalling significant wealth. But from a thermal standpoint, those glass windows were revolutionary. You could have light and still maintain warmth, which transformed the livability of interior spaces during winter months. The heating systems in better-off urban houses might include multiple hearths, one for cooking, another for heating the main living space, perhaps a brazier or two for supplemental heat in particular rooms. These households could afford more fuel and could invest in more sophisticated fire management. Some urban houses by the later medieval period had early chimneys, stone or brick structures that directed smoke out of the building rather than letting it accumulate and eventually filter through the roof. Chimneys were expensive to build but dramatically improved air quality and fire safety. Now we get to the gentry and minor nobility, people living in manor houses rather than castles, but definitely at the upper end of medieval society. Manor houses in the 13th century were typically built of a mixture of materials, stone foundations and possibly stone first floors, timber framed upper stories, tile roofs rather than thatch. These were substantial structures, often with multiple rooms including a great hall for public and social functions, private chambers for family, kitchens, storage rooms, and various outbuildings. Impressive certainly, and markers of significant status. But here's where the paradox starts becoming obvious. Manor houses were frequently less thermally efficient than peasant cottages despite being built with superior materials at greater expense. The Great Hall, the centerpiece of any manor house, was a large, high-ceiling space designed to impress visitors and accommodate gatherings. It might be 30 feet wide, 60 feet long, and 20 feet high. That's a lot of volume to heat, and medieval heating technology wasn't up to the task. A large hearth in the centre of the hall or against one wall could make the immediate vicinity comfortable, but the extremes of the hall would remain cold. The high ceiling meant warm air rose up and was effectively wasted because nobody was using that upper volume for anything except making the space look impressive. The window, but even with glass, and not all manor house windows had glass, many use shutters or oiled cloth, windows are thermal weak points. Glass doesn't insulate as well as a thick wall, and window frames create air leakage paths. The more and larger your windows, the more heat you're losing. So the manor house's impressive glazed windows that announced the owner's wealth were simultaneously making the building harder to heat. The stone construction of better manor houses and castles created another thermal problem. Stone has high thermal mass, which sounds good. It absorbs and stores heat. But it also conducts heat quite well compared to materials like thatch and wattle and daub. And stone's thermal mass works against you in winter if your building can't generate enough heat to actually warm up that mass. A stone building in winter is basically a cold sink. It absorbs whatever heat you generate and radiates it back outside, requiring constant, substantial fire to maintain any warmth at all. Let's talk specifically about castles now, because this is where the thermal paradox reaches its peak. The nobility who lived in castles were the wealthiest, most powerful people in society. They had access to unlimited resources by medieval standards, and they lived in what were essentially refrigerators for most of the year. The irony is almost painful. The typical medieval castle featured thick stone walls, often 6 to 10 feet thick at the base, which were excellent for defence but terrible for thermal comfort. Stone walls that thick take ages to warm up and conduct heat steadily to the exterior. The rooms in castles were large because scale impressed visitors and demonstrated wealth. The ceilings were high, often with stone vaulting that looked impressive but created vast volumes of space to heat. Windows, even when glazed, were set into such thick walls that they created cold zones around themselves where drafts would circulate. The great halls in castles were architectural statements designed to awe and intimidate. They might be 50 feet wide, 100 feet long, 30 or 40 feet high. The idea was to show that you could afford to build and maintain such a space, that you commanded resources on a scale that ordinary people couldn't comprehend. And you could certainly build impressive great halls with medieval technology. What you couldn't do was heat them adequately. Even with massive fireplaces, and castle fireplaces could be enormous, with openings 10 feet wide and hearths that could accommodate whole tree trunks, the extremes of a castle great hall in winter would be bitterly cold. The heating strategy in castles relied on enormous open fireplaces that consumed staggering quantities of wood. We're not talking about modest cooking fires. We're talking about fires that required servants to constantly feed them with logs, that created roaring flames visible across the hall, that represented fuel consumption that would bankrupt a peasant household in a week. And even with these massive fires, thermal comfort was limited. The area immediately around the fire would be almost uncomfortably hot. Move 20 feet away and you'd need heavy woolen clothing to stay warm. The far corners of the hall? Forget it. The chimneys in castles were major architectural features, often multiple stone structures rising stories high to properly vent the massive fires below. Building and maintaining these chimneys required skilled masons and represented significant investment. But while they solved the smoke problem, unlike peasant cottages where smoke just accumulated until it filtered out, they also represented major heat loss points. All that warm air rising up the chimney was heat that wasn't warming the building. The living, private chambers, the lords' and ladies' personal rooms, would be smaller spaces that could actually be heated somewhat effectively with braziers or smaller fireplaces. People would retreat to these chambers for sleeping and private time, essentially abandoning the great public spaces when thermal comfort was needed. The Great Hall would be used for dining, audiences, public business, times when you had to be there for social or political reasons and just endured the cold. Important events in winter might warrant firing up the Great Hall's fireplaces regardless of cost, but day-to-day living happened in smaller, more manageable spaces. The use of textiles for insulation reached its peak in castle settings. Tapestries weren't just art. They were functional insulation that helped make stone walls less hostile to human comfort. A thick tapestry hanging on a stone wall created an insulating air gap, while also adding a psychological sense of warmth through its visual richness. Wealthier nobles invested fortunes in tapestries, not just for status display but because they genuinely improved living conditions. You'd see multiple layers of fabric hanging on walls, tapestries on the outside, lighter fabrics behind them, all creating dead air spaces that reduced heat loss through stone. The floors in castles presented another thermal challenge. Stone floors, while durable and impressive, were absolutely frigid in winter. The wealthy would cover them with layers of rushes and herbs, just like peasant cottages, but they'd also add woven mats, carpets if they could afford them, and layers of other textiles to create insulation between human feet and cold stone. The very wealthiest might have wooden floors installed over the stone in private chambers, creating an air gap that provided insulation. But the main public spaces typically remained stone, cold and impressive in equal measure. The servants in castles had their own thermal challenges. While the lord and lady might retreat to relatively comfortable private chambers, servants often slept in groups in whatever spaces were available. Storage rooms, the great hall after the fire died down, chambers above the kitchen where rising heat provided some warmth. The social hierarchy in castles was literally thermal. Your status determined how close you got to heat sources and how comfortable your sleeping arrangements were. The kitchen in a castle was typically separated from the main building for fire safety reasons, sometimes in a completely separate structure connected by a covered walkway. This made kitchen staff more comfortable. They worked in the warmest space in the castle complex, but it meant that food was cold by the time it reached the Great Hall, another reminder that castle living prioritized display and defense over comfort. The logistics of moving hot food through drafty corridors or across open courtyards in winter meant that castle dining involved cold food as a routine matter. The wealthy who owned multiple properties would move between them, partly following the agricultural calendar and administrative needs, but also seeking better climate and comfort. Summer might be spent in a breezy hill country manor. Deep winter might mean moving to a more sheltered, smaller residence that could actually be heated. The largest, most impressive castles might be reserved for important occasions and favourable seasons, not constant occupation. The peasant in their cottage stayed put. They didn't have options. Now let's directly compare thermal comfort across social classes, because the results are fascinating and counterintuitive. Take a cold January night with temperatures around freezing and wind howling. The peasant family in their wattle and daub cottage with livestock in the byre end, a modest fire on the hearth, thick thatch overhead, and everyone sleeping together for warmth is probably maintaining interior temperatures in the mid-50s Fahrenheit, maybe even into the low 60s. Not luxuriously warm by modern standards, but livable and comfortable enough for sleep if you've got blankets. The noble in their castle, even with massive fires burning, is probably experiencing temperatures that vary from uncomfortably hot near the fire to below 40 degrees in the far reaches of the Great Hall. Their private chamber, if they've retreated there and lit a brazier, might achieve temperatures similar to the peasant cottage, but at vastly greater fuel cost and only in a small portion of the total building. The castle, despite its impressive scale and expensive construction, is fundamentally colder than the humble cottage, at least measured by average interior temperature and thermal comfort for the inhabitants. This paradox stems from medieval society's priorities. Castles weren't built for comfort, they were built for defense and status display. The ability to construct and maintain a massive stone fortress demonstrated power and wealth. The fact that it was cold inside was an acceptable trade-off, or perhaps wasn't even consciously recognized as a trade-off because everyone assumed that impressive buildings were inherently better. The possibility that simpler buildings might be more comfortable probably didn't occur to most people, or if it didn't matter because comfort wasn't the primary goal. The peasant cottage, by contrast, was built solely for function. Nobody was trying to impress anyone or make defensive statements with their wattle and daub walls. The goal was survival and basic comfort using minimal resources. This focus on pure function, combined with appropriate technology and materials, resulted in buildings that were actually quite effective at their primary purpose of shelter. The cottage didn't look impressive. It didn't signal status or power, but it kept you warmer than a castle, which is darkly amusing when you think about the social hierarchy that placed castle dwellers at the top and cottage dwellers at the bottom. The awareness of this paradox in medieval society is hard to gauge. Written records from nobles occasionally mention the cold in their castles, complaints about drafts, references to wearing multiple layers of clothing indoors, descriptions of seeking heat from fires. Whether they recognized that their peasants were warmer in their cottages is less clear. The social divide was so stark that direct comparison probably didn't happen. Peasants didn't tour castles to discover they were freezing. Each class lived in their own environments and accepted them as natural and appropriate to their station. The technological solutions attempted to address castle heating show awareness of the problem, if not necessarily understanding of the underlying thermal principles. Later, these developments show that comfort was valued and that builders were trying to improve it, but they were working within constraints of materials, technology, and social expectations about what impressive buildings should look like. The introduction of glazed windows was a genuine improvement that primarily benefited the wealthy who could afford them. As glass, this narrowed the comfort gap between wealthy and poor to some degree. A manor house with glazed windows had real advantages over a cottage with shuttered openings, but it didn't. The use of bed curtains and bed enclosures in medieval upper-class housing was partly about privacy, but largely about creating a small enclosed space that could be warmed by body heat. A four-poster bed with heavy curtains closed around it was essentially a micro-environment, a room within a room where you could achieve reasonable warmth, even if the surrounding chamber was cold. The wealthiest nobles slept in what were effectively fabric tents erected around their beds, trapping body heat and creating tolerable sleeping conditions, even when the room's ambient temperature was frigid. The role of clothing in thermal management varied by class, but represented a significant strategy for everyone. Peasants wore wool, practical, warm, and available. The wealthy wore multiple layers of elaborate garments that were partly status display and partly functional insulation. The concept of indoor and outdoor clothing was less distinct in medieval times. You dressed warmly because buildings were cold, and you might add or remove layers as you moved between colder and warmer areas of your dwelling. The wealthy could afford better fabrics and more layers, which helped compensate for their colder living spaces. The health implications of these different thermal environments are interesting to consider. The peasant in their smoke-filled but relatively warm cottage faced different challenges than the noble in their cold stone castle. Respiratory problems from smoke exposure would have been common among peasants. The wealthy would have suffered more from cold-related ailments, joint problems, respiratory infections from cold and damp, general physical discomfort. The evolution of domestic architecture through the late medieval period and into the early modern era shows gradual convergence toward more thermally efficient designs even among the wealthy. The Great Hall tradition declined as smaller, more manageable rooms became preferred for daily living. Fireplaces became more sophisticated, with designs that radiated heat more effectively into rooms rather than just up chimneys. The Tudor period saw increased use of brick, which has better insulation properties than stone. Gradually, comfort became more valued relative to pure display, and buildings evolved to reflect that shift in priorities. But throughout the period we're discussing, the 13th century and the core medieval period, the paradox remained. The wealthiest people in society lived in the coldest, most uncomfortable buildings, while the poorest lived in structures that, however humble, were actually more effective at providing thermal comfort. This inverted relationship between wealth and comfort is so counterintuitive to modern people that it's worth sitting with for a moment. We're used to assuming that money buys comfort, that the wealthy are always more comfortable than the poor. Medieval England shows that this isn't automatically true. It depends on what you're buying and what technologies are available. The lesson from this class comparison is that appropriate technology, building methods and materials suited to their purpose and available resources, can outperform impressive but less appropriate alternatives. The peasant cottage represented hundreds or thousands of years of refined vernacular architecture, evolved through trial and error to maximize function using available materials. The castle represented the application of military and status priorities to domestic architecture, and while it succeeded admirably at being impressive and defensible, it failed at being comfortable. Neither was wrong exactly. They were optimized for different goals, but if your goal was thermal comfort on a cold January night, you'd rather be a peasant in a cottage than a noble in a castle. And there's something satisfying about that. Medieval society was brutally hierarchical, with nobles exercising enormous power over peasants who had few rights and limited freedoms. But at the end of a cold day, when everyone went home, the peasant got to be warmer than the lord. The humble materials and simple construction that marked peasant poverty were also more effective at their core purpose than the expensive stone and elaborate construction that marked noble wealth. Justice isn't exactly the right word for this dynamic, but there's a pleasing symmetry to it. Wealth bought status and power but didn't buy comfort. Not in medieval England, not with medieval technology. The physics of heat transfer and insulation didn't care about social hierarchy, and sometimes that meant the person at the bottom of the social order was sleeping better than the person at the top. That's not a bad note to end on when thinking about medieval life, a reminder that wealth and power don't solve every problem, and that simple solutions to basic needs can be more effective than elaborate alternatives, regardless of how much they cost. So we've talked extensively about the buildings themselves, the materials, the techniques, the thermal strategies, the social organization, but we haven't really addressed the people who actually knew how to turn raw timber and stone into habitable structures. The carpenters and masons who possessed the specialized knowledge that made medieval construction possible. These weren't just laborers following instructions. These were skilled craftsmen with years of training, sophisticated understanding of materials and structures, and a whole culture of professional practices that included everything from joinery techniques to superstitious rituals. Welcome to the world of medieval building trades, where knowing how to cut a proper mortise could mean the difference between a building that stood for centuries and one that collapsed in the first strong wind. Let's start with carpenters, because timber construction was the foundation of most medieval English building, and carpentry was one of the most essential and respected trades. A skilled carpenter in 13th century England would have undergone years of apprenticeship, typically starting around age 12 or 13, and training until their early 20s. That's roughly a decade of education, which tells you immediately that this wasn't simple work that anyone could pick up quickly. The knowledge being transmitted was extensive, complex, and largely tacit. You learned by doing under supervision, not by reading manuals that didn't exist in accessible form anyway. The carpenter's toolkit was deceptively simple by modern standards, but represented a significant investment and took considerable skill to use effectively. You'd have several axes of different sizes and weights for rough shaping, felling, and splitting. Adze saws, though medieval saws were less effective than modern ones and used primarily for cross-cutting. Augers for drilling holes. Chisels in various sizes for cutting mortises and pairing joints. A mallet for driving chisels. Measuring, maybe some chalk or charcoal for marking cuts. That's basically it. With this relatively minimal toolkit, a master carpenter could fabricate complex timber frames that would support buildings for centuries. The techniques for working timber started with tree selection, which we touched on earlier with cruck frames but applies broadly to all timber work. Carpenters needed to understand wood, how different species behaved, how grain direction affected strength, how trees that grew in different conditions produced different characteristics. An oak grown slowly in dense forest would have tight grain and excellent strength. The same species grown rapidly in open conditions would be softer and more prone to splitting. Medieval carpenters learned to read trees the way modern people read product specifications, understanding from observation and experience what would work for which purposes. The conversion of logs into usable timber was done with axes and wedges, splitting along the grain rather than sawing across it. This riving technique is actually superior to sawing for creating structural timber, because it follows the grain, producing pieces that are less likely to split or warp in use. A medieval carpenter could look at a log, visualize how the grain ran through it, and split out beams that were naturally straight and strong because they aligned with how the tree grew. It's an impressive skill that takes years to develop and has largely been lost in the modern era of milled lumber. The joinery techniques used in medieval carpentry deserve detailed attention because they represent sophisticated engineering executed with hand tools. We've mentioned mortise and tenon joints already, but let's go deeper into how these actually worked and why they were so effective. A mortise is a cavity cut into one piece of wood. A tenon is a projection cut on another piece that fits into that cavity. Simple in concept, remarkably complex in execution. The wall, the bottom needs to be flat. All of this achieved by hand with chisel and mallet, working an oak that's hard and unforgiving. The process for cutting a mortise started with marking out the location and dimensions carefully. You'd drill out most of the waste with an auger, leaving a rough cavity. Then you'd use chisels to pare away material, working from both sides if possible, until you had a clean rectangular cavity of the precise dimensions needed. The tenon was created by saw cuts to establish shoulders, then paring away waste with chisel or axe to create the projection. The fit was critical. Too tight and you'd split the timber trying to assemble it. Too loose and the joint would be weak. Medieval carpenters developed an eye for correct fit that's hard to explain but absolutely crucial to their craft. The variety lap joints, where two pieces overlap and are notched to fit flush together. Scarf joints for joining timbers end to end when you needed longer pieces than available trees provided. Dovetails, though these were less common in structural work and more often appeared in furniture and fine joinery. Each joint type had specific applications where its characteristics made it the best choice, and knowing which joint to use where was part of a carpenter's expertise. The assembly marks found on medieval timber frames are fascinating evidence of construction processes and have become a specialized field of study for architectural historians. Before raising a frame, carpenters would mark each joint pair with matching symbols so they'd know which tenon went into which mortise during assembly. These marks were usually Roman numerals, but you also see various geometric symbols, simple scratches, or unique carpenter's marks. The system was simple. Matching marks meant matching pieces, but it was essential when you're fabricating dozens or hundreds of joints that all look similar but are actually custom fitted to specific locations. These assembly marks tell us several things about medieval construction practices. First, all the fabrication was done on the ground in a carpenter's yard, not at height during assembly. Second, the marks show that carpenters thought systematically about how frames would be assembled, creating numbering schemes that made logical sense. You'd number joints sequentially along a beam, or use a consistent system for identifying which frame you were working on. Third, the survival of these marks on building timbers centuries later shows that they were considered part of the permanent structure, not temporary notes to be erased. The carpenter's marks, personal symbols that individual craftsmen used to identify their work, are a different category from assembly marks but equally fascinating. These might be initials, geometric designs, or unique symbols that a carpenter consistently used across different projects. Finding the same carpenter's mark on multiple buildings tells you that the same craftsman worked on those structures, allowing historians to trace careers and identify the work of specific masters. Some carpenters' marks show up repeatedly across a region, suggesting successful practitioners whose services were in demand. The significance of these personal marks went beyond just identifying who did the work. In a largely illiterate society, these marks served as signatures, carrying legal and professional weight. A carpenter's mark on a beam could settle disputes about who was responsible for construction, who should be paid for work, or whose workmanship was at fault if something failed. The marks were also a form of professional pride. Putting your mark on work announced that you were confident in its quality and willing to stake your reputation on it. The superstitions and rituals associated with carpentry are where we see the intersection of practical craft and medieval worldview. Foundation rituals were common, making offerings or saying prayers before beginning construction to ensure the building's success and the inhabitants' good fortune. The idea that buildings had spiritual dimensions wasn't metaphorical to medieval people. They believed the protective symbols carved into timber frames show up frequently in surviving medieval buildings and reveal the beliefs that guided construction practices. You find geometric patterns believed to ward off evil, sometimes even crude figures or symbols whose meanings are lost to us but clearly had significance to the people who carved them. The timing of construction work was sometimes influenced by beliefs about auspicious and inauspicious days. Certain saints' days might be considered favourable for beginning building work. Moon phases might influence when timber was felled, or when certain operations should be undertaken. We can't always distinguish between practical considerations and superstition. Maybe you really did get better results felling timber during certain moon phases because of sap content, or maybe it was just belief. Either way, medieval carpenters operated within a framework where practical technique and spiritual protection were intertwined. The training of apprentice carpenters transmitted not just technical skills, but also this entire cultural framework. An apprentice learned joinery techniques, certainly, but also when to make offerings, which saints to invoke for protection, how to mark timbers to ensure good fortune. The master-apprentice relationship was intense and comprehensive. You weren't just learning a trade, you were being initiated into a professional culture with its own knowledge, practices, and beliefs. This helps explain why medieval crafts were organized into guilds that controlled training and entry. They weren't just protecting economic interests, they were guarding specialized knowledge that took years to acquire. The use of preservatives and protective treatments for timber shows medieval carpenters' understanding of wood deterioration and their efforts to extend timber life. Pine tar and pitch were commonly used to coat timbers that would be exposed to weather or ground contact. These sticky, dark substances created a water-resistant barrier that significantly slowed decay. The smell was pungent and the material was messy to work with, but it worked, extending timber life by years or decades. You can still see evidence of tar treatment on surviving medieval timbers, dark coatings that have protected wood for centuries. The production of tar and pitch was a specialized process, usually done by people who made it their trade. You'd burn resinous wood, pine or fir, in controlled conditions that allowed tar to collect while minimizing complete combustion. The resulting tar was thick, sticky and rich in preservative compounds. Pitch was tar that had been further processed to drive off volatile components, making it even more durable and water-resistant. Both materials were valuable trade goods that carpenters would purchase as needed for projects requiring enhanced wood protection. The application of tar wasn't uniform across all timbers. You'd focus on areas most vulnerable to decay: post feet that contacted stone foundations, sill beams close to ground level, any timber exposed to weather. Interior structural timbers often received no treatment beyond maybe some surface smoothing, which was fine because interior conditions didn't promote rapid decay. This selective treatment made economic sense. Tar cost money, so you used it where it would do the most good rather than coating everything indiscriminately. Now let's turn to masons, because while timber construction dominated domestic building, stonework was essential for higher status structures, foundations, and certain architectural features. Masonry was arguably an even more specialized trade than carpentry, because stone is less forgiving than wood, and mistakes are harder to correct. A mason's apprenticeship was similarly lengthy, and the skills required were different but equally complex. You needed to understand stone, how to read it, how to work it, how to set it so it wouldn't crack or shift. The stone types used in medieval England varied by region based on local geology. Limestone was common and relatively easy to work. It could be shaped with chisels and held details well. Sandstone was another popular choice where available. Granite was used in some regions but was harder to work and required more skill and effort. Flint was used extensively in areas like East Anglia, where other stone was scarce. Though working with flint required completely different techniques than working with more conventional building stones. Medieval masons had to know their local materials and adapt techniques accordingly. The quarrying and initial working of stone was rough labour, but selecting stone for specific purposes required expertise. A mason could look at a quarry face and identify stone that would work well, checking for cracks, inclusions, grain direction, all the factors that determined whether a block would be stable or prone to splitting. This knowledge came from experience and observation, from seeing which stones in earlier buildings had performed well and which had failed. Medieval masons were practical geologists who understood stone behaviour even if they couldn't explain the underlying mineral chemistry. The tools of the mason included various hammers and chisels for rough shaping and fine detail work. A mason's hammer wasn't like a carpenter's. It was heavier, designed to drive chisels through stone rather than wood. Chisels came in many forms: points for rough work, tooth chisels for texture, flat chisels for smooth surfaces. There were saws for stone, though they worked differently than wood saws, cutting through abrasion with sand and water rather than with teeth. Measuring and marking tools were crucial: squares, levels, plumb lines, dividers for laying out work. All relatively simple tools that required skill to use effectively. The techniques for dressing stone, shaping it to require dimensions and surface finish, were fundamental to masonry. You'd start rough shaping with a heavy hammer and point chisel to remove excess stone. Intermediate work with tooth chisels to get close to final dimensions and create texture. Final smoothing with flat chisels to achieve the desired surface finish. For high-quality work, you might spend hours on a single stone, working it until every surface was precisely square and smooth. The laying of stone in walls required understanding of how loads distributed and how to create stable structures. The basic principle was that stones should be laid on their natural bed, the orientation they had in the quarry, which provided maximum strength. Joints should be staggered so vertical cracks didn't align, which would create weak planes. Each stone should bear on at least 2 stones below it and support at least 2 above. Following these principles, a skilled mason could create walls that would stand for centuries without mortar, though mortar certainly helped and was used extensively in medieval construction. The mortar used in medieval masonry was typically lime mortar, a mixture of lime, sand, and water that hardened through reaction with carbon dioxide from the air. Making good, the lime needed to be properly slaked, mixed with water and allowed to react fully. The sand needed to be clean and appropriately graded. The proportions needed to be right for the intended purpose, different mixes for different applications. A mortar that was too rich in lime would crack and shrink. Too lean, and it wouldn't develop strength. Getting it right required experience. The mason's marks found on medieval stone buildings served similar purposes to carpenter's marks, identifying who did the work, tracking payment for piecework, marking specific stones for assembly in complex structures like arches or vaulting. Mason's marks tend to be more elaborate than carpenter's marks, often quite decorative, possibly because stone provided a better surface for carving detailed symbols, and marks lasted longer on stone than on wood. The study of masons' marks allows historians to track individual masons' careers across multiple projects, sometimes spanning decades and hundreds of miles. The organisation of masons into lodges, workshop and guild structures that controlled training, set standards and regulated the trade, was more formalised than for carpenters, probably because major stone buildings required coordinated efforts by multiple masons working together. Cathedral construction or major castle building might employ dozens of masons simultaneously, requiring organisation and hierarchy to coordinate their work. The master mason was essentially the architect and construction manager, designing the structure and overseeing its execution. Journeyman masons did the bulk of the work under supervision. Apprentices learned the trade through years of observation and increasing responsibility. The trade secrets of medieval masons were jealously guarded, transmitted through lodge systems and protected from outsiders. This secrecy has led to considerable speculation and mythology about hidden masons' knowledge, much of it probably overblown. But there certainly were techniques and knowledge that masons preferred to keep within their trade, advantageous for maintaining high wages and professional status. The exact recipes for the best mortars, the tricks for working particular stone types, the methods for achieving certain decorative effects, these would have been trade knowledge, shared among masons but not broadcast to everyone. The superstitions and protective practices of masons paralleled those of carpenters but had their own flavours. Foundation deposits, objects buried during construction to bring good fortune, are found in medieval buildings, ranging from coins to animal remains to various symbolic items. Orientation of buildings according to sacred geometry or astronomical alignments reflected beliefs about cosmic harmony and divine order. Protective symbols carved into stone, religious imagery, geometric patterns, even crude faces believed to ward off evil, show masons incorporating spiritual protection into their physical work. These weren't optional niceties, they were essential steps in completing a building properly. A structure that hadn't been properly blessed was incomplete, vulnerable to misfortune. Modern people might view this as superstitious nonsense, but for medieval builders and occupants, it was as important as making sure the roof didn't leak. Physical and spiritual integrity were equally necessary. The collaboration between carpenters and masons in buildings that combined both materials required coordination and mutual respect between trades. A manor house with stone foundations and walls but timber roof structure needed both crafts working together. The masons would build up to the wallhead level, leaving proper seating for the timber plates that carpenters would install to carry the roof frame. The carpenters would need to work from scaffolding erected by or in cooperation with masons. Both trades had to understand enough of the other's work to coordinate effectively, even if they specialised in their own materials. The social status of skilled craftsmen in medieval society was respectable but not elevated. A master carpenter or mason could make a good living, own property, have apprentices and perhaps employees. They weren't wealthy by noble standards but were comfortably middle class by medieval terms. They had specialised knowledge that was valued and which gave them leverage in negotiations over pay and conditions. But they were still working people, earning wages or piecework payments, dependent on finding employment, subject to the economic ups and downs that affected everyone except the landed nobility. The mobility of skilled craftsmen was considerable, particularly masons working on major projects. A cathedral construction might draw masons from across the country, or even from other countries, creating a cosmopolitan workforce that exchanged techniques and knowledge. This mobility meant that architectural ideas and construction methods spread relatively quickly across medieval Europe. A mason who worked on a church in France might later work on a castle in England, bringing continental techniques and ideas with him. This international exchange of craft knowledge helped drive architectural evolution during the medieval period. The legacy of medieval craftsmen survives in the buildings they created, many of which still stand and function centuries later. When you examine medieval timber frames or stonework, you're seeing the direct product of individual craftsmen's hands and minds. There's something profound about that continuity. Timber they shaped still carries loads, stone they dressed still bears weight, joints they cut still hold together. The buildings are their monuments, more enduring than most written records. The loss of much medieval craft knowledge through changing technology and building practices represents a genuine break in tradition. When construction shifted to modern methods, the accumulated wisdom of centuries of hand-tool craftsmanship became obsolete practically overnight. We can reconstruct some of it through experimental archaeology and study of surviving work, but the tacit knowledge, the feel of how timber behaves under your chisel, the sound of stone as you work it, the 100 small judgments that experts make instinctively, much of that is gone. Modern craftspeople working in traditional methods are essentially reinventing knowledge that was once common among working builders. The relevance of medieval craft practices to modern concerns about sustainability and quality construction is increasingly recognized. Hand craftsmanship, local materials, techniques adapted to specific conditions rather than standardized universal methods. These medieval characteristics are being reconsidered as advantages rather than quaint historical curiosities. The buildings medieval craftsmen created have lasted longer than most modern structures will, used entirely renewable and non-toxic materials, and were built with techniques that could be learned through apprenticeship, rather than requiring expensive education and equipment. That's worth learning from, even if we're not going back to hand-hewn timber frames as standard practice. So when we talk about medieval building, we need to remember the human expertise behind it. The cruck frames and stone walls and carved timbers we've been discussing throughout this entire series weren't produced by generic medieval people as some undifferentiated mass. They were created by individual craftsmen who trained for years, developed sophisticated skills, worked within professional cultures with their own practices and beliefs, and took pride in their work. The carpenter who cut those mortises, the mason who dressed those stones, the thatcher who laid that roof, they were real people with names and lives and skills that commanded respect. Their work was their legacy, and that legacy includes not just the buildings themselves, but the demonstration that humans with hand tools and accumulated knowledge can create functional, durable, beautiful structures that serve their purposes for centuries. That's not primitive. That's mastery, and it deserves to be recognized as such. So we've journeyed through 12 chapters of medieval English winter survival, from earth-bermed cottages to stone castles, from wattle and daub to thatch roofs, from livestock heating to communal fires. We've explored techniques that kept people alive through months of cold weather, using nothing but local materials, accumulated knowledge, and community cooperation. And if you've been paying attention, you've probably noticed some recurring themes running through all of this. Patterns that show up again and again in how medieval people approach the challenge of not freezing to death. These patterns aren't random. They represent fundamental principles of survival and building that have relevance extending far beyond medieval England, principles that we do well to remember even in our modern, centrally heated world. The first and most obvious principle is adaptation to local conditions. Medieval builders didn't have the option of importing materials from across the globe or using standardized building systems designed for generic conditions. They had to work with what was available locally: the stone in their region, the trees in their forests, the clay in their soil, the reeds in their marshes. And rather than treating these local materials as limitations, they developed sophisticated techniques for using them effectively. The result was buildings that were deeply adapted to their specific environments, using materials that had evolved to survive in those exact conditions. This adaptation wasn't just about materials, it extended to design choices shaped by local climate, topography, and weather patterns. Villages in exposed upland areas clustered tightly for wind protection, and built with steeper roof pitches to shed heavy rain. Lowland settlements might spread out more and use different construction techniques suited to flatter terrain and milder conditions. Coastal buildings had extra thick thatch and additional structural bracing to handle harsh winds coming off the sea. Every region developed its own building vernacular that reflected centuries of experience about what worked in that specific place. The modern building industry has largely abandoned this principle of local adaptation in favor of standardized systems that can be deployed anywhere. We build essentially the same house in Minnesota as in Arizona, just adjusting the HVAC system to handle different temperature ranges. This works, sort of, but it requires enormous energy inputs to compensate for buildings that aren't adapted to their environments. The medieval approach, deep adaptation to local conditions using local materials, is looking increasingly sensible as energy costs and environmental concerns mount. The second principle is the value of thermal mass and insulation working together. Medieval buildings used thick walls, substantial roofs, and strategic placement of mass materials to moderate temperature swings and retain heat. The wattle and daub walls, the deep thatch, the earth floors, all of these provided both insulation value and thermal mass that absorbed and slowly released heat. Modern building has tended to separate these functions. We have insulation in walls and mass materials like concrete used primarily for structure. But the medieval integrated approach actually works quite well. The passive heating and cooling that thermal mass provides is something modern, sustainable building movements are rediscovering. A building with substantial thermal mass will naturally moderate temperature extremes, staying cooler in summer by absorbing heat during the day and releasing it at night, staying warmer in winter by storing heat from sun or fires and releasing it slowly. Medieval builders understood this empirically and built it into their structures as a matter of course. The fact that modern passive house design is moving back towards similar principles suggests that maybe those medieval builders knew something worth remembering. The third principle is that community organization and cooperation improve survival outcomes for everyone. The clustered villages, shared walls, communal resources, mutual aid systems, all of these meant that medieval people faced winter as communities rather than as isolated individuals. Your ability to survive wasn't just about your own building and resources. It was about how your house related to your neighbours' houses, whether the village maintained communal fires and protected spaces, if people helped each other with construction and maintenance. This communal approach provided thermal benefits through shared walls and wind protection, but also social and economic benefits through shared labour and resources. Modern culture, at least in much of the developed world, has moved strongly toward individualism, everyone responsible for their own shelter, comfort and security, with minimal dependence on neighbours or community. We've gained privacy and autonomy, but lost the efficiencies and resilience that come from cooperation. Medieval villages were more efficient than equivalent numbers of isolated homesteads would have been, and they were more resilient because resources and knowledge were pooled. When one family faced crisis, the community could help. That kind of social insurance is harder to achieve when everyone lives in isolation. The fourth principle is that appropriate technology often beats advanced technology, at least when appropriate means suited to available resources and actual needs. The medieval building techniques we've discussed weren't the most advanced technology available. Even in the 13th century, there were more sophisticated building methods known in various parts of the world, but they were appropriate to medieval English conditions. They worked with available materials, required skills that could be transmitted through apprenticeship, solved the actual problems people faced, and didn't require resources or infrastructure that didn't exist. This concept of appropriate technology is crucial for understanding why medieval buildings worked as well as they did. The techniques weren't primitive versions of better modern methods that people used because they didn't know any better. They were optimized solutions to specific problems given specific constraints. A wattle and daub wall was appropriate for a timber frame building in a location with available clay, willow, and agricultural waste. It wouldn't work everywhere, and it isn't the best solution for every situation, but for its specific context, it was excellent. Modern technology is often inappropriate. It requires resources, energy, and infrastructure that may not be sustainably available, and it solves problems in ways that create new problems. The fifth principle is that maintenance and ongoing care are essential for longevity. Medieval buildings that have survived for centuries didn't do so by being maintenance-free. They survived because they were continuously cared for. Thatch was replaced when it wore out. Daub was patched when it cracked. Timbers were treated when they showed signs of decay. Foundations were adjusted when they settled. The buildings were understood as living systems requiring attention rather than static objects that could be built once and forgotten. This maintenance-intensive approach seems like a disadvantage from a modern perspective where we expect things to last without attention, but it actually contributed to longevity because problems were caught and addressed before they became catastrophic. Modern building culture expects materials to be maintenance-free or low maintenance, and we're often disappointed when they don't live up to that expectation. But maybe the medieval approach, accepting that buildings need regular care and building that expectation into how we think about construction, is actually more realistic. Buildings inevitably deteriorate. Materials age and fail. The question is whether you're paying attention and addressing problems as they develop, or ignoring them until catastrophic failure forces expensive repairs or replacement. Medieval people chose continuous, modest maintenance over deferred problems, and their buildings lasted longer as a result. The sixth principle is that local knowledge and traditional practices embody accumulated wisdom that shouldn't be dismissed lightly. Medieval builders knew which trees made good cruck timbers, when to harvest thatch materials, how to mix daub for optimal properties, where to site buildings for wind protection, all knowledge gained through generations of experience and observation. This wasn't written in textbooks or based on scientific theory. It lived in the practices of working craftspeople who learned from masters who learned from their masters going back through centuries. Modern building often dismisses traditional practices as outdated or primitive, assuming that newer methods must be better because they're newer. But traditional practices that survived for centuries probably survived because they worked. They represent successful solutions to real problems, tested over time and refined through countless iterations. Some traditional practices are genuinely inferior to modern alternatives, certainly, but some are actually superior or at least comparable when you account for total costs including environmental impact and long-term sustainability. The rush to abandon traditional methods in favor of modern materials and techniques has sometimes been premature and short-sighted. The seventh principle is that comfort and impressive appearance don't always align, and optimizing for one may sacrifice the other. This was the lesson from comparing peasant cottages to noble castles. The humble, practical cottage built purely for function was often more comfortable than the impressive castle, built to project power and status. Medieval society chose to build castles anyway because comfort wasn't the only goal, or even the primary goal for those structures. But the example reminds us that chasing impressiveness or status can lead to solutions that don't actually serve human needs as well as simpler alternatives. Modern architecture often falls into the same trap. Buildings designed to look striking or innovative that don't actually work well for their occupants. Glass towers that are expensive to heat and cool, houses with dramatic features that sacrifice livability, designs that prioritize appearance over function. The medieval lesson, that buildings should be judged by how well they serve their purposes rather than how impressive they look, is worth remembering. A cottage that keeps you warm has achieved its primary purpose even if it doesn't win architectural awards. A castle that looks magnificent but leaves you shivering has prioritized the wrong objectives. The legacy of medieval building practices in modern English architecture is more substantial than most people realize. The timber frame tradition continued well into the early modern period and never completely died out. Many English buildings from the Tudor period and later used timber framing techniques that trace directly back to medieval practices. The distinctive black and white timber frame houses that are iconic of certain English regions are descendants of medieval building traditions, just with some technical refinements and stylistic evolution. Even modern British construction shows influences from medieval practices in attitudes toward materials, craft, and durability. The conservation and restoration of historic buildings in England has required rediscovery and preservation of medieval building techniques. You can't properly maintain a medieval timber frame building using modern methods that don't understand how the original structure was designed to work. This has created a small community of traditional craftspeople who've learned medieval techniques, not as historical curiosity, but as practical necessity for keeping historic structures functional. These modern practitioners of ancient crafts represent a direct link to medieval builders, using tools and methods that would be recognizable to 13th century carpenters and masons. The sustainable building movement has increasingly looked to traditional and vernacular building practices, including medieval techniques, as models for low-impact construction. Straw bale building, cob construction, timber framing, natural insulation materials, all of these contemporary alternative building methods draw inspiration from traditional practices that predate industrial construction. The earthbag and rammed earth builders rediscovering the virtues of earth construction are following paths that medieval sunken house builders walked routinely. The revival of interest in craft and hand-tool woodworking includes people learning traditional joinery techniques for both practical and aesthetic reasons. The mortise and tenon joints that medieval carpenters cut by hand are now appreciated as embodying principles of good design, efficient use of materials, distribution of loads across large surface areas, repairability and adaptability. Modern woodworkers creating furniture or structures with these traditional joints are connecting to a craft tradition that extends back through centuries, and many report that working this way provides satisfaction that power tool construction doesn't quite match. The educational value of studying medieval building is substantial and extends beyond just historical interest. Understanding how people solved fundamental problems of shelter with limited resources and technology provides perspective on our current practices and possibilities for future development. When you understand that comfortable, durable buildings can be created using local materials and relatively simple techniques, the modern building industry's dependence on global supply chains and complex technology looks less inevitable and more like a choice with trade-offs that maybe aren't all positive. The environmental sustainability of medieval building practices is particularly relevant given current climate concerns. Buildings constructed entirely from renewable local materials using human labour and hand tools had essentially zero carbon footprint beyond the food calories consumed by workers. The materials were biodegradable, non-toxic and recyclable. Old thatch became compost. Worn-out timber could be burned for fuel or repurposed. Even wattle and daub could be broken down and returned to soil. The contrast with modern construction using concrete, steel, petroleum-based materials, and energy-intensive manufacturing is stark. The social organisation that supported medieval building, apprenticeship systems, guild structures, community labour networks, provided pathways for knowledge transmission and skill development that worked without requiring extensive formal education. A young person could enter a building trade through apprenticeship and emerge after years of training as a skilled craftsperson, capable of supporting themselves and contributing valuable services to their community. The knowledge was practical and immediately applicable rather than abstract and theoretical. Modern education has moved away from this model toward classroom-based learning and certification systems, which work for some knowledge domains but may be less effective for hands-on craft skills. The resilience of medieval building systems is worth emphasizing. Their ability to function with locally available materials and distributed skills meant communities weren't dependent on external supply chains or specialized experts who had to be imported. A medieval village had within itself the knowledge and resources to build and maintain structures adequate for survival. This kind of resilience is valuable in any era, but particularly so when thinking about adaptation to uncertain futures, where current systems might not be reliably available. The limitations of medieval building also deserve acknowledgement. These systems worked for medieval populations and circumstances, but wouldn't necessarily scale or translate directly to modern contexts. Medieval England had population densities much lower than current levels, so extensive use of timber and thatch was sustainable. Not clear that modern populations could be housed using medieval methods without devastating remaining forests. Medieval people accepted levels of smoke, smell, and physical discomfort that modern people wouldn't tolerate, so their solutions might not meet current expectations for indoor air quality and thermal comfort. The point isn't to romanticize medieval building or suggest we should return to it wholesale, but to learn from the principles and see what's applicable to current circumstances. The integration of medieval building principles with modern technology offers interesting possibilities. You could imagine buildings that combine medieval thermal strategies, thick walls with thermal mass, compact designs, clustered layouts for wind protection, with modern materials and systems where they provide clear advantages. Passive heating and cooling through thermal mass and insulation, supplemented by efficient mechanical systems for extreme conditions rather than relied on constantly. Local materials used creatively alongside modern materials where those provide clear benefits. Community planning that facilitates cooperation and shared resources while respecting modern desires for privacy. The goal wouldn't be to recreate medieval buildings, but to learn from their principles and apply them in contemporary contexts. The archaeological study of medieval buildings continues to reveal new information about construction techniques, spatial organization, and material culture. Each excavation or detailed examination of surviving structures adds to our understanding of how these buildings were conceived, constructed, and used. The picture that emerges is increasingly detailed and sophisticated, showing medieval builders as skilled problem solvers working within their constraints to create effective solutions. The experiential understanding that comes from actually working with medieval building techniques, building reconstructions using traditional tools, processing natural materials, provides insights that can't be gained from just studying historical records or examining buildings. Organizations and individuals doing this hands-on work report consistent findings that medieval techniques work better than expected, that the buildings are more comfortable than anticipated, that the methods make sense once you understand them in practice. This experiential validation of historical practices is important confirmation that we're correctly understanding how these systems functioned. The preservation question, how to maintain surviving medieval buildings while keeping them functional for modern use, requires balancing historical authenticity with practical needs. A medieval building being used as a residence or workplace today needs to meet modern safety and comfort standards in ways that may require modifications to historical fabric. Finding appropriate compromises that preserve significant features while allowing necessary adaptations is an ongoing challenge that requires understanding both medieval building systems and modern requirements. The best solutions respect historical materials and techniques, while carefully introducing modern improvements where genuinely needed. The documentation of medieval building practices for future generations is important work that combines historical research, traditional craft knowledge, and modern recording technologies. Creating detailed records of how medieval buildings were constructed, what techniques were used, how materials were processed. All of this helps ensure that knowledge isn't lost as practitioners retire or pass away without passing on their skills. The documentation takes various forms: written descriptions, photographs, videos, CAD models, even virtual reality reconstructions that allow people to experience medieval buildings and construction processes in immersive ways. The inspiration that contemporary architects and builders draw from medieval practices varies from direct imitation to subtle influence. Some deliberately use traditional techniques in new buildings, creating structures that would be recognizable to medieval builders even if they incorporate modern elements. Others take principles from medieval building: local materials, passive heating and cooling, community integration, and express them through contemporary design. Both approaches represent meaningful engagement with historical building traditions and suggest that those traditions continue to have relevance for current practice. The human connection across centuries that medieval buildings provide is perhaps their most profound legacy. When you stand inside a timber frame building and run your hands along timbers shaped by medieval carpenters, when you see masons' marks carved by craftspeople dead for 700 years, when you experience the spatial quality of a medieval great hall or the cozy intimacy of a small cottage, you're connecting directly with people who lived almost unimaginably long ago. They're not just names in books or statistics in historical studies. They're real people whose work survives and whose choices shaped spaces that we still occupy. That continuity is precious and rare, and medieval buildings provide it in ways few other artifacts can match. So what should we take away from this long exploration of medieval winter survival and building practices? First, that medieval people were neither primitive nor helpless. They were sophisticated problem solvers who created effective solutions to real challenges using available resources and accumulated knowledge. Second, that many medieval building principles remain relevant and valuable: adaptation to local conditions, community cooperation, appropriate technology, passive thermal management, maintenance and care, respect for craft knowledge. Third, that modern building practices, while achieving important goals of comfort and efficiency, have also abandoned useful principles that might help address current challenges of sustainability and resilience. The medieval builders who clustered their cottages for wind protection, who stuffed gaps with moss and wool, who shared walls with neighbours, who kept livestock inside for heat, who layered thatch 2 feet thick, they knew what they were doing. They were working with profound understanding of thermal physics, material properties, and human needs, even if they expressed that understanding through practice rather than theory. Their buildings worked, often remarkably well, and many have survived for centuries as testament to the skill of their creators. As we face our own challenges of climate change, resource constraints, and the need for more sustainable living systems, there's wisdom to be found in studying how people in the past solved similar problems. Not to simply copy their solutions — our circumstances are different and we have capabilities they lacked — but to learn from their principles and approaches. Medieval people adapted to their conditions rather than trying to overpower them with technology. They built communities that cooperated for mutual benefit. They used local resources creatively and efficiently. They accepted that living sustainably meant working within limits rather than exceeding them. These are lessons worth learning, or relearning, as we think about how to build and live in ways that work for both human needs and planetary health. The medieval period isn't some golden age we should try to recreate. It had brutal inequalities, limited opportunities, harsh conditions, and short lifespans for most people. But it also had examples of humans living in closer harmony with their environments, building with renewable materials, creating community structures that provided mutual support, and developing craft traditions that produced work of lasting quality and beauty. That's worth studying, worth learning from, and worth trying to integrate into how we approach current challenges. So as you drift off to sleep tonight, maybe in your modern, insulated, centrally heated home that would seem like absolute luxury to a medieval peasant, spare a thought for those long-ago people who figured out how to survive brutal winters with nothing but local materials, accumulated knowledge, and each other. They built the cottages and castles whose ruins and restorations we still visit today. They developed techniques and traditions that influenced building practices for centuries afterward. They left a legacy of practical wisdom about human shelter that continues to have relevance even in our very different world. They survived, they adapted, and they created. That's worth remembering and honouring. And on that note, it's time to let you get some rest. We've covered a lot of ground together over these 12 chapters, from earth-bermed cottages to stone castles, from cruck frames to communal fires, from livestock heat to mason's marks. You've learned about wattle and daub, about thatch that was 2 feet thick, about moss stuffed in gaps and wool hung on walls, about villages clustered tight against the wind. You've seen how medieval people survived winter not through brute force or advanced technology, but through cleverness, cooperation, and deep understanding of their environment. I hope you found it fascinating. I hope you've discovered that history is more interesting than textbooks sometimes make it seem, that people in the past were smarter and more capable than we often give them credit for, and that there's real wisdom to be found in studying how humans solved fundamental problems throughout history. Most of all, I hope you sleep well, warm and comfortable in your modern dwelling, with new appreciation for the incredible ingenuity it took for our ancestors to achieve even basic comfort with the limited resources they had available. Sweet dreams, everyone. May your sleep be warm, your dreams be pleasant, and your appreciation for medieval ingenuity be just a little bit deeper than it was before we started this journey together. Good night,